it is generates slow disposal issues. Then with the biological treatment method, that is slow, sensitive and ineffective for non-biodegradable pollutants. Then for the membrane filtration, it is always costly and less effective for all the pollutant removals. Then the chemical oxidation is also a very process, and as a chemist we also follow this chemical oxidation, but it requires large amount of reagents and it generates the secondary pollutants which are also harmful. Then why adsorption? Adsorption is simple, economical and scalable, high efficiency even at low pollutant concentration. We can do the adsorption and separate the pollutants. So why photolytic catalytic degradation? That utilizes renewable solar and visible light. So solar radiation mainly consists of visible light. So it also consists of UV light. So we can degrade the pollutants using UV radiation as well as visible radiation. So besides the pollutants they break the pollutants into harmless end products. So the end products after mineralization is CO2, carbon dioxide and water. This minimizes secondary waste compared to the other treatment. So why this photocatalytic degradation is preferable? Because this minimizes the secondary waste, which is from the chemical oxidation. As we saw, we got the secondary pollutants, but in photocatalytic degradation we will not get the secondary pollutants. So the key advantage, adsorption concentrates pollutants on the surface and photocatalytic degradation degrade them completely. So the first step is the adsorption, then the next step is the photocatalytic degradation in the presence of UV visible or in the presence of visible UV light or visible light. So these are the different mode of photocatalytic removal of pollutants. First one is here is adsorption. The adsorption we all know there are two types, one is chemisorption, one is physisorption. Then we have coagulation, flocculation, and this one is very important, that is advanced oxidation process. In advanced oxidation process we got the hydroxyl radicals, and that radical helps in the scavenging or in killing or degrading the pollutants. Then we have biological treatment as I mentioned, and also the membrane filtration. So these methods are versatile, they are used for the organic pollutant removal methods. Then what is the challenges in remove the organic pollutants? In the adsorption, as I discussed, it is a simple method, cost effective, efficient, and removal is a very easy, but the limitation is only transfer the pollutants require further treatment. So you will separate the pollutant, but again the question is what you will do with that pollutant. Second is the photocatalytic degradation, that is the advanced oxidative process. Here the breakdown, we have break down the all the pollutants into CO2 and carbon dioxide and water. So these are the mineralized product, but the limitation is the electron hole recombination. This is low efficiency and costly post process. So there is we will see what is the electron hole recombination in the next slide. Then the overall challenges is neither adsorption nor photocatalysis alone is sufficient. So you have to integrate or improve the nanostructural materials that is required. So a material which can adsorb the pollutant and later on it can degrade it, that kind of material is essential for this kind of study. Then the mechanism of photocatalytic degradation. So the photons, the light consists of photons, that photons got adsorbed on the semiconductors. We know what is the difference between semiconductor, conductor and insulator. So the semiconductor where the band gap is below 3 electron volt, there the visible light will do the catalysis, and if it is above 3 electron volt, then the UV light will do the catalysis. So the semiconductor that absorb light with energy greater than the band gap. So first of all, if you design a new catalyst, you have to measure the band gap in order to find direct or indirect band gap using the Kubel-Monk function, what is the band gap of that solid. Then depending on that you can see if it is less than 3 electron volt the band gap of the solid, then it can be useful for the visible light photocatalysis, and if it is greater than 3 electron volt, then it will be then UV light photocatalysis can be done. The electron hole generation. So there is a excitation of electron. So here in this picture you have a valence band, you have a conduction band. From when the UV light or visible light fall on your semiconductors, there is generation of the electron transit from the valence band to the conduction band. So the hole is created in the valence band, and you have electrons in the conduction band. So the excitation electron from the valence band to conduction band, leaving a hole in the valence band. The charge carrier migration, the electron and hole migrate to the catalyst surface. So once the electrons and hole that they are generated on the catalyst, then they migrate to the catalyst surface. So on the surface the hole which is created in the valence band that reacts with the water to give you the OH radical, the hydroxyl radical, or the electron which goes to a conduction bed that reacts with the oxygen to give you the superoxide radical. So this superoxide radical and this hydroxyl radical, they are using, though they are helping in the degrading the organic pollutants. The pollutant degradation reactive oxygen species. So these hydroxyl radical or superoxide radical, they are known as reactive oxygen species, ROS. They reduce or they degrade the pollutants into harmless product such as CO2 and water. The recombination, the problem is there sometimes if since the band gap between the valence band and conduction band is not that much in semiconductor, it is high in the insulator and is very low, and it is not there in the conductor, but in semiconductor though the gap is there, but the gap is not that large. So there is a chance of there is some combination of electron and hole pair, they may combine, so that will reduce the efficiency. So we have to also be careful about that. Then the photocatalysis is a sustainable choice. It is solar energy driven. So if you can do the catalysis in the presence of solar light, then it will be very useful. It is green, renewable and cost effective. Then the complete mineralization, as I mentioned, you will get CO2 and product and water. There is no secondary pollutants getting formed in this process. They are applicable for dye, pharmaceutical pesticides and heavy metals. So in our laboratory we are doing these methods to degrade the dye, different kind of anionic cationic dyes, and also the chromium reduction. Chromium 6 is a very big problem in nowadays. So we are also reducing the chromium 6 and also some pesticides and also some antibiotics. So this works synergistically with the adsorption for higher efficiency. The limitations, the electron hole recombination gives us low efficiency, so we have to overcome that limitation. Then poor adsorption capacity of many photocatalysts. It is not that whatever catalyst you will design, all catalyst will adsorb a large amount of the pollutants. It is not true. So the poor adsorption capacity is also a problem. Then the limited visible light absorption in conventional oxides. For suppose you prepared oxide like titanium dioxide, which has a high band gap, then that will not absorb the solar radiation, visible light radiation. Since solar radiation consists mainly, major part is visible light, so if you can do the catalysis in visible light presence, it will be more beneficial. So the research need development, the design of nanostructure photocatalyst with enhanced surface area and adsorption site, reduce electron hole recombination, extended visible light adsorption. This is our main aim. So this ensure the stability, reusability and low toxicity for the practical application. Then if you look at the only adsorption, if I say only by adsorption I will want to remove the pollutant, it can reduce the toxicity, but at the same time your pollutants will be there, they will not be degraded, so you have to treat them again. So the limitations with the adsorption is this only captures the pollutants temporarily, does not destroy them. Efficiency depends on the adsorbent surface area and porosity. If you have a high surface area, if you design a catalyst with a high surface area, then the adsorption will be more. And if your catalyst has some porosity, it is a porous material, so by doing the BET, you can measure the surface area as well as porosity, BET with the help of BET, and then you can say whether my design catalyst can adsorb the pollutants or not. They may require frequent regeneration for repeated use. So if you want to prepare a catalyst, then you want to reuse it. So then at that time or at that point, first you have to remove whatever the pollutants has been adsorbed on the surface, then only you can reuse it. So the research needs development, design nanostructured adsorbents with high surface area. So our first challenge is to prepare a catalyst with a high surface area and active sites. Then the combined adsorption and photocatalytic, as I mentioned, adsorption has certain demerits. So if I can adsorb some of my pollutants on the catalytic surface and then do the degradation, then it will be more beneficial. Then ensure reusability, low toxicity and scalability. These are also we have to ensure that the catalyst which we prepare, it can be reusable, it should have low toxic level, and we can do the scalability also in order to treat a large amount of pollutants. So the mechanism of adsorption, so organic pollutants are removed from wastewater by adsorption through multiple interaction like electrostatic, hydrogen bonding, pipe stacking and the pore filling of the adsorbent surface. This is just a slide to show the mechanism. So now the designing of oxide nanostructures, which is now today my topic of discussion for adsorption and photocatalytic degradation. we synthesized various oxide nanostructures like spinel, perovskites, different type of rare earth oxide, different type of transition metal oxide, and we looked at its composition, its structure, and its morphology, and also its surface area. Then we treat with target pollutants are organic dyes, pharmaceuticals, and some heavy metals. We employ microbe assisted hydrothermal synthesis or solvothermal synthesis in most of my whatever the case studies I will show after this. All the catalysts we have prepared by microbe mediated synthesis. So microbe mediated synthesis, these are easy method, this is a green synthesis, and it is short time duration. You can prepare the catalyst within 10-minute duration, the catalyst is prepared. So the focus on dual function materials like adsorb pollutants first, then degrade them photocatalytically. And our main aim is to evaluate the adsorption kinetics and isotherms, the photocatalytic degradation efficiency, and the reusability and the stability of the catalyst. So these are some of the materials which we have prepared in the lab, and we are studying it for the removal of dye. I will show you 3 cases. One case is for the we prepared a catalyst and look at the adsorption. Second case, we prepared a catalyst and look at the photocatalytic degradation in the presence of visible light, and in the third case it is in the presence of UV light. So first of all, we prepared the cobalt ferrite COFe2O4. This is a spinel structure with cubic phenol structure, and we did the XRD, SEATM and BET surface area analysis in order to calculate its surface area. Then we look at the application for the adsorption of the organic dyes. So this is the 2 materials we prepared. One is nickel ferrite, one is cobalt ferrite, in order to check whether both the ferrite, if you want to, if you think or I will think that all the ferrites which is possible to prepare are all are efficient catalyst or not. That's why we prepare 2 catalysts to compare. One is nickel ferrite, one is cobalt ferrite, and we calculated and we saw the catalytic study. Only cobalt ferrite gave us the good result, nickel ferrite didn't give us the result. And the BET surface area shows for cobalt ferrite the surface area comes something around 77 meter square per gram, and the particles here you can see there are very small particles around 10 to 20 nanometer, as you can TM you can see it. And the morphologically they are very much agglomerated, because in the microwave in a short time duration you are heating the sample. That's why maybe the SEM sample, the morphology there is little bit of agglomeration is there, but if you look at the EDAX, all the stoichiometry is maintained there. Then we did the removal of the dyes. Here we have taken 2 dye for our system. One is erichrome black tea, one is bromophenol blue, and we varies the different concentration of dye we have taken. Also we varied catalyst dose, we varied the amount of the dye. So adsorbent and adsorbate both concentration we varied, and it is the time profile adsorption graph for 20 to 80 mg per liter of EBT. For that we tested our catalyst, and for the bromophenol blue from 5 to 20 mg per liter and dye we have used it. And as you can see, with increase in the catalyst dose, the adsorption increases. So the increase in the adsorption of dyes with increase in adsorbent dose is primarily attributed to increase in number of available site. So if you increase the dose, increase the amount of catalyst, definitely the amount of available adsorption site will increase. So that's why it has increased. So in the right hand side we have the percentage of adsorption of EBT and BRB. So we can, as a function of cobalt ferrite, with increase in cobalt ferrite and the adsorption, how adsorption varies, we have shown that. Then we did the isotherm and kinetic studies. The isotherm studies, we fitted the graph with Langmuir isotherm, Friend-Lewis and Tumpkin isotherm. So it best fitted. Oh, sorry, the R square value is missing here. So the best fitted line is with the Langmuir adsorption isotherm, which shows it is a monolayer adsorption. So the maximum monolayer adsorption capacity we calculated for both erichrome black tea and bromophenol blue, and it was found for erichrome black tea is 82.6 milligram per gram of the dye is getting adsorbed, and for bromophenol blue it is 25.6 milligram per gram. The calculated QE value from second order kinetic model agreed reasonably well with the experimental value, and the maximum adsorption capacity indicated the adsorption follows a second order kinetics. So if you look at the kinetic model, we fitted the data with pseudo first order and pseudo second order kinetics, but it fitted with the pseudo second order kinetics. This work has been published in Advanced Powder Technology. Then we prepared cerium vanadate CE vehicles, and we found its band gap around 2.8 electron volt, As I mentioned, if the band gap is less than 3 electron volt, then it is visible light for. So we are doing the degradation of EOS in yellow using this visible light driven photocatalysis using cerium 100 as our catalyst. So this is the cerium 100 in the tetragonal phases, it has crystallized. You can see it is matching with the JCPDS file, and we compare the XRD pattern before and after degradation. So there is no change in the XRD as well as FTIR. You can see before or after degradation. That means dyes has already been degraded. There is no dye on the surface of the catalyst. So after doing the experiment, we have removed the catalyst, and again we have analyzed using the XRD and FTIR, and we can see exactly the pattern is matching the initial phase as the before the experiment. So that confirms that there is no dye is now adsorbed on the surface. So our surface, all the dye, we are able to remove it by this mineralization or degradation using the catalyst. Then this is the TM for the cerium 100. These are rod shaped molecules, and here the band gap is less than 3 electron volt, which I want to point it out as 2.8 electron volt. The band gap, we did the diffuse reflectance solicited UV, and we measured the band gap for this material. Then we did the degradation test. First we put our catalyst and the dye, and we kept it for equilibrium for 30 minutes in dark, so that whatever the maximum adsorption can take place, it will be getting adsorbed. Then after that we put the light on that, and we saw the degradation, and the degradation effect on initial concentration, catalyst dose and pH we varied. And as you can see, the catalyst got more degradation in the pH around 2. So in the acidic pH it got more degradation, because in acidic pH our surface is mainly negatively charged. So the anionic dye they got adsorbed on that, and dye got degraded. This paper has been accepted and we published in Journal of Physics and Chemistry of Solids. So next we move to zirconium dioxide, ZrO2. So ZrO2, it is again a tetragonal phase. We prepared this using the microwave solvothermal method, where we use 1,4-butanediol instead of water as our solvent. Then we use the organic dye for the degradation, and this is the ZrO2. So we prepare ZrO2 by two methods, one by chemical method and one by microwave method. So to see what are the changes in the morphology or structure, if any there, by the two different methods. Then we did the SEM and TM analysis for that, and this is a XPS analysis where we can see the zirconium oxidation state as well as the binding of oxygen is there with the zirconium. And again we took a dye, and we look at the catalyst dose and the initial dye concentration, how with the increase in the catalyst dose the dye degradation takes place. So defined amount of catalyst, we vary the catalytic adsorbent amount and also the adsorbent amount in order to fix in order to come to a conclusion what is the best for our system. Then we look at the effect of pH, effect of scavenger, and we did the reusability test. In the effect of scavenger, as you can see, we used isopropyl alcohol, sodium azide and formic acid. Isopropyl alcohol that quench the OH radicals, the sodium azide that quench the superoxide radicals, and the formic acid that quench any hole present in our system. So as I mentioned, in the conduction band you have electrons, and in the valence band you have holes. So the hole get quenched by the formic acid. But as you can see, with the formic acid, there is no decrease in the percentage of degradation. That means the degradation percentage is very high. So the mechanism is not going through quenching of the holes. So mainly the mechanism is going through either the electron which is generating on the surface of the conduction band, that is forming the OH radical or superoxide radical, and those free radicals, they are degrading our pollutants or dye in this case. Then we are doing the reusability test. After the 3 cycles also, as you can see, the percentage of the catalyst efficiency remains same, hardly it has any decrease. So we compare these 3, cobalt ferrite, cerium 100 and ZrO2, we prepare all these three by microwave synthesis method, and in the first one we check the adsorption, in the second catalyst we look at the photocatalytic degradation using visible light, then in the third case we did the UV light photodegradation using zirconium oxide, catalyst is zirconium oxide, just because they vary in their band gap varies from one to another. Then currently this is an unpublished work which we are now writing a paper. This is the hydrothermal fabrication of reduced graphene oxide supported at plasmodium oxide, which is a rare earth oxide, for efficient removal of ciprofloxacin. So ciprofloxacin, we know antibiotics, and antibiotics, they are also threat to the ecosystem and human health. So our solution is, we are proposing that reduced graphene oxide since it has a high surface area, that graphene oxide and PR6O11, that is successfully we have prepared it, and we are looking at the removal of the ciprofloxacin, which is the antibiotic. So we have fitted our data with the Langmuir model, and the maximum adsorption capacity you can see is 85.5 milligram per gram. The kinetics also, the pseudo second order model, it is also fitting. Then from the thermodynamics, we have calculated the delta G and delta H value. Delta G, you can see it is a negative delta G, that means it is a spontaneous reaction. The adsorption mechanism, electrostatic interaction, pi-pi stacking, and hydrogen bonding, that is responsible for this adsorption. Then we have also checked the reusability, the 85% capacity after 4 cycle. After the 4 cycle of repeated cycle, still the catalyst has retained the 85.5% efficiency as a reusability. Then it is a robustness also we have checked. So this is the preparation of graphene oxide from graphite. By exfoliation we have prepared this. Then we have prepared RGO and PR6O11. This is reduced graphene oxide. So we have reduced the graphene oxide and we have made the composite with PR6O11. So this is the process. Simple Homers method, we prepared the graphene oxide. Then we did the XRD, FTIR, then TEM analysis. Then we can see the small particles, well dispersed particles of PR6O11 on the surface of the graphene oxide. Then the performance test, if you compare PR6O11 and RGO PR6O11, with pristine PR6O11 only 62% CIP ciprofloxacin removal is possible, but with RGO composite we could remove the 88% of CIP. So the uniform dispersion of PR6O11 nanoparticle on RGO increases the accessible surface area and porosity. The pi-pi interaction from RGO strengthens the binding with aromatic ring of ciprofloxacin. Oxygenated group on RGO facilitates the hydrogen bonding and electrostatic interaction. The RGO support prevents the aggregation, exposing more active sites. The mechanical and chemical stability of the composite improves reusability across the cycle. So these are the, as I mentioned, we have followed the pseudo second order model, and the rapid initial adsorption, the equilibrium reaches in 160 minutes. The isotherm, the Langmuir model is the best fitted model, and the mechanism is, we have you can see 85.5 milligram per gram has been the adsorption capacity, maximum adsorption capacity. And here we have done the Venn-Topf plot. From the Venn-Topf plot you can calculate the delta H and delta S. From the intercept you will get the delta S, and from the slope you will get delta H. Then delta, you know, delta G equal to delta H minus T delta S, so you can calculate the free energy change. So we have calculated the free energy change of the system for at different temperature. So this is the summary of this, whatever done in this work. So we have seen the delta H is negative, that it shows the exothermic process. Delta is also less than 0. This decreases that system randomness during the adsorption. That key takeaway is CIP adsorption onto RGPO is a spontaneous, exothermic and thermodynamically favorable, but efficiency reduced slightly at higher temperature. If you increase the temperature, then definitely the catalytic activity is getting down. Then the future perspective in nanostructure oxide catalysts, we are now working on the interface engineering, the heterojunction, and we are also using some dopants in order to activate the catalyst more, and in order to suppress the electron hole pair combination. Then the hybrid multifunctional materials, visible light active catalyst is our main aim, that all the catalysts they should adsorb in the visible light region, because the solar light, as I mentioned, solar light mainly consists of visible light. Then the reusability and stability, that we are checking again and again. This green synthesis method, if you will be able to do it, then that will be low cost, environmental friendly approach. In conclusion, oxide nanostructure synthesis by microwave assisted synthesis route are fast, they are scalable and they are eco-friendly. We demonstrated adsorption and photocatalysis both. Adsorption, the rapid pollutant capture, and photocatalysis completely demineralization. Then cobalt ferrite, CeVO4 and ZrO2, we showed and we compared their high efficiency, stability and reusability. This provides a promising pathway for sustainable and wastewater treatment. Future scope lies in the development of multifunctional solar active and scalable oxide nanostructure that integrate adsorption and photocatalysis for real wastewater treatment. So, I would like to acknowledge Ravenshaw University from where I came in and the research collaborators and students. Thanks to the Higher Education Government of Odisha and BARC for the funding. Thanks to my students and thanks to the all organizers and the students and the audience. Thank you.
Wonderful. So, it's open for discussion. Any question? Professor Biswak? Yes, Professor De.
Sir.
If you permit.
Sir, please.
It is a nice work, very nice work. Just I have one query. The mechanism, the Langmuir adsorption that you are talking about, do you think that really Langmuir works here? Or it is a maybe some that is called extension of the Langmuir adsorption isotherm, maybe that is a Langmuir-Hinsen-Lund mechanism or something like that. Because it is the main thing is that it is not purely Fiji sorption. It is not a it is a sorption, Fiji or chemical, I think so.
Sir, it is not a chemisorption for sure. It is not a pure chemisorption because we don't have a acid-base interaction on the surface.
Because the delta G value that you are showing,
Sir,
it falls within the range of sorption process, if I am sure. So do you think, my question is that, do you think that really Langmuir works here?
Sir, we compared Langmuir, Friendlich and we compared the Tompkin model, and among these three models, there are many other models as you were mentioning. Our modified Langmuir model is also there. In these three models, the best R square value that fitted with the graph is for the Langmuir. That's why we were claiming that it is Langmuir. But yes, as you said, Langmuir means it is a single layer adsorption. It may not be a single layer adsorption. There may be, but it is not also a multi-layer. So BT is not there. No question of going to a multi-layer system. But it is a single layer adsorption. But maybe there are one or two stack of layers on each other that we have not. We don't have that much sophisticated instruments to analyze it. Analyze the surface.
With increase in temperature, the adsorption is decreasing.
Yes. No, I am not questioning the value. I am just questioning, this is just introspection. The Langmuir himself, you see the next 4 kind of model came. Extension of the Langmuir model. Okay.
It is there, sir.
So,
yes, sir.
So pure Langmuir may not be, we are mentioning, all papers are mentioning Langmuir model. I am also mentioning. But my introspection is that, because sir is also there. Okay, is it a pure Langmuir? I don't, it is a all extension of the, because Langmuir to 1916, 1918, 1922. So 3 papers published in this.
The monolayer is inconsistent with
that
the
is
observations that they are getting.
Yes. Thank you.
They will unravel the mystery behind, right?
So maybe we have to analyze the surface of the catalyst again with some.
No, I agree with the value.
No, sir, it's okay. So you are right.
Thank you.
Any other question? If no, I have a question. Professor Pari, have you tested the degradation products of the dye? You mentioned once that carbon dioxide, water, that what are the degradation products have you measured from the dye?
Many times I have told my student to do the GCMS, and we have the facility with us also, but the degraded product still now we have not analyzed.
And in a lighter vein, if carbon dioxide goes, again it will produce more greenhouse gases. So degrading,
but still carbon dioxide is safer than that pollutants.
Pollutants gone.
Yeah.
But greenhouse.
But pollutants is not on the catalyst surface that we have identified. But what happened at the pollutants? Pollutants really it has gone to CO2 water, or it is some other byproducts are there. We have not analyzed the solutions.
Okay. Thank you for the excellent talk.
Thank you, sir.
Thank you, sir, for such an inspiring. Thank you, sir, for inspiring. Thank you, sir, for inspiring us with your passion for spectroscopy. Your presentation has motivated us to explore new areas of research and application. Thank you. Now I invite Chairperson Professor Dr. Sudhanshu Shekhar Tripathi, the convener Professor Dr. Deepa Nag, Organizing Secretary Professor Dr. Abani Kumar Sahu to felicitate Dr. Pari. Please give a huge round of applause. Spectroscopy is the journey of discovery and taking us deeper into the mystery of the physical world. Now with this, let's know about our next speaker, Professor Dr. Bijayalakshmi Jaina.
Dr. Jaina is an associate professor and head of the Department of Chemistry at Utkal University, Bhubaneswar. She earned her PhD from IIT Kanpur and joined Utkal University in 2010. Her research focuses on nanostructured materials and electrocatalysis. She has published 23 research papers, supervised 2 PhD scholars, 20 MPhil scholars, and currently guided 5 research scholars. Dr. Jaina has served as University nominee to the Homeopathy Medical College and Hospital, member of the Scientific Committee and Jury for the International Science. Let's welcome Dr. Jaina to the stage.
Pointer. चलिए नेक्स्ट जाओ तो नेक्स्ट
सीटीटी लिखे सीडी मैम
देखें कोटा चिपियो
এইটা হচ্ছে প্রিভিয়াস এটা হচ্ছে নেক্সট
Namaskar to all. A very warm afternoon, good afternoon to all. At first, I must thank Deepa ma'am and Avani sir for inviting to this international seminar, and I must congratulate sir and ma'am and all the faculty members for organizing this international seminar. Today I am going to speak about the topic of my research, that is electrocatalysis. Since this seminar is based on optical spectroscopy, in the second part I will discuss some of the molecules which showing the photophysical properties. So, at first the work which I am doing right now, I will discuss this part. So, nanostructured materials as electrocatalyst for water splitting reaction. Why electrocatalysis of water is important? We know our present generation, we all require, present or past, we all require energy for everything. So, we need energy, and normally we are getting energy from the non-renewable sources like oil, coal, natural gases. These are the sources of energy from, and these are depleting very quickly because of the population. So, we need to have one alternative to this source of energy, and the best alternative is production of the energy from water, sun, wind. These are the some of the renewable sources from which we can get energy, and it is not depleting, and the energy from the energy we get from these sources are non polluting, or it is greener. As a result, there is no pollution and green environment we could get by utilizing this energy. So, electrocatalytic water splitting, in this process we use water to split water into hydrogen and oxygen, and this hydrogen can be used as a fuel for our future energy requirement. So, in this some potential is what applied to water to break the water into hydrogen and oxygen. If that hydrogen can be stored, then it is a green hydrogen we can produce. So, for this we use 3 electrode system where there are 3 electrodes, and catalyst, we require one catalyst for the breaking of water to enhance the rate of the this reaction, we require a catalyst. So, we use a electrode system, electrochemical workstation we use, where 3 electrode systems were used to carry out this reaction. So, Toyota Caosa motor, they have claimed that they have generated an hydrogen fuel based car with which can run 650 km with refueling time of 5 minutes. Advantage of this car is that they use the hydrogen, which is a green hydrogen that is produced from the water. So, in order to break water, we require some potential, that is 1.23 volt, and because of some resistance factor, this voltage is much more than 1.23. So, we need some catalyst which is such much efficient, so that it can decrease the potential, that resistance factor it can cut out. So, we need to prepare some catalyst which is highly active, stable and low cost. And in order to enhance the activity of the material, we can have various, we can do various things like creation of vacancy in the material. We can use to enhance the property of the your catalyst. We can vary the shape and size by using different surfactants. Even by doping and composite formation, the enhancement of the activity of the catalyst can be done. So, first I will talk about the role of vacancies in enhancement of activity. That means, the product to break the water into hydrogen and oxygen, we require one catalyst whose potential should be near to 1.23. So, we have to create some vacancy in the material, so that we can enhance the activity of one catalyst. So, vacancies, what is vacancy? It is nothing but the absence of atoms in a material. Vacancy is nothing but absence of atoms in a material. And normally every materials have some minimum concentration or equilibrium concentration of vacancy, and with the non-stoichiometric compound this vacancy creation can be done much more compared to the equilibrium concentration. So, we take the advantage of the non-stoichiometric compounds to create the vacancy in a material. As a result, we can use that vacancy to enhance the activity of a catalyst. What is the advantage of vacancy? It can act as an active site, it forms new gap states in the electrocatalyst, it lowers the free energy value for a reaction. Normally, there are various during the reaction or hydrogen when it breaks to hydrogen and oxygen, water when it breaks to hydrogen and oxygen, there are various intermediates that were formed, that is hydroxyl radicals, oxyhydroxide radicals, oxides radicals, and these radicals free energy can be is decreased when vacancy is created in a material. There are various methods to create vacancy in a material like laser fragmentation, plasma etching, chemical vapor deposition and many others. But for our method to create a vacancy in a material, we used a very simple method, that is called aqueous chemical reduction method. In this, it is just using the reducing agent, within half an hour we can create vacancy in a material. So, we do not have to use a laser fragmentation, chemical vapor deposition, costly methods, we do not have to use that method to create vacancy. It is a simple half an hour treatment method which gives you the result just by using one reducing agent. So, here I will discuss the role of selenium vacancy and iron doping in nickel selenide in water oxidation reaction. Since I have told you that water when it splits it produces oxygen and hydrogen. So, we have one oxygen evolution reaction and one hydrogen evolution reaction. So, in this material what we have done, we have created one selenium, we have created a selenium vacancy in iron doped nickel selenide. So, method of synthesis, that we have used 0.7 moles of nickel, 0.3 moles of iron and selenium calculated amount to produce nickel iron selenide in that ratio. But we named it as iron doped nickel selenide because when we did ICP-OES, this ratio did not maintain. So, we have to call it as iron doped nickel selenide, although we have used 0.7 and 0.3 nickel iron, 0.7 and 0.3 nickel for the preparation. So, we have named the material as nickel 0.7, iron 0.3 selenide. So, for the synthesis, first we have prepared that calculated amount, we took nickel and iron. By using a hydrothermal method, we could produce nickel iron layer double hydroxide. This layer double hydroxide, when treated with selenium powder following a sombothermal method, we could get nickel 0.7, iron 0.3 selenide. Then for vacancy creation, it is a very simple easy method. The material was kept in sodium borohydride solution and we could find from characterization that some vacancy or selenium vacancy were created. What we did, we kept the material in sodium borohydride solution for 30 minutes stirring, and from the characterization we could get there was selenium vacancy in the material. These are the XRD pattern. The lower one is nickel selenide, and when we introduced iron to that, it matches the crystal structure of nickel selenide. That means iron doping on the material does not change the crystal structure of nickel selenide, and we could get various, we could get a beautiful flower structure for both nickel iron selenide and vacancy selenium nickel iron selenide. even vacancy material corresponds to the crystal structure of nickel selenide. That means iron doping and vacancy creation does not change the crystal structure of nickel selenide. ADAX confirms the presence of all this nickel, iron, selenium in the material. So, XPS confirms the presence of all these elements, that is nickel, iron, selenium in the material. Now, from the XPS study we confirm the presence of selenium in it. What you can see in the upper AB is vacancy material and the lower one are the parent material. So, you can see when parent material, that is CD, the nickel iron selenide, when treated with sodium borohydride, there is an increase in peak area of nickel 2 and iron 2 in vacancy material, that is AB. That nickel 2 and iron 2 increase only suggests that there is a selenium vacancy. Why I am telling so? Because when the nickel concentration is number 2 concentration is increasing. How it is increasing? When we treat the material with sodium borohydride, it is a reducing agent. What it does? It reduces iron plus 3 and iron plus nickel plus 3 state to iron plus 2 and nickel plus 2. As a result of which the nickel 2 and iron 2 concentration is increasing compared to 3 states of iron and nickel. When the plus 2 charges is increasing, that means there is a overall decrease in positive charge in the material. When there is a overall decrease of the positive charge in the material, in order to maintain the electrical neutrality, some selenium or anion has to remove, so that there is a electrical balance in the material. So, in that is why the selenium get removed to maintain the electrical neutrality, and as a result the selenium vacancy is confirmed from the XPS spectra. These are certain characterization of electrochemical oxygen evolution reaction. You can see the light is not coming. So, the light ta pade. लाइट टा गोटे आसनी ये तो आगू पड़छ हम ना लाइट कहीं जोड़ हाँ ओके so as you can see in plot 1 A, as you can see in the graph A, as I have told you, normally some electronic instruments, when it require lower potential, it is a good one. That means when the splitting of water requires the energy which is nearer to 1.23 would be the better one, because the resistance factors it can decrease. So, when we have done one linear shift voltammetry plot, that is A, we could see the less potential is required by the vacancy material compared to the others. The lower the potential, greater is the activity of the material. So, vacancy material you can see it requires less potential, that is 200 some the value I can see, but it requires a less potential compared to the others. Similarly, B is the indication of the at current density 10 and 20 milliampere per centimeter square, what are the potential requirement of the material, and vacancy material was showing potential less in both 10 and 20 milliampere per centimeter square current density. C refers to the Tafel slope, which indicates the rate of the reaction, and lower the rate of Tafel value, greater is the rate of the reaction, which was derived from the Butler-Volmers equation. The D plot indicates the Faradic efficiency of the material, which indicates the flow of electrons, each of flow of electrons in a electrochemical reaction, and we have calculated the Faradic efficiency to be 92.3% for this material. And E represents the impedance value. Impedance is nothing but the resistance and lower is the resistance, higher will be the conductivity, and in one normally one electrochemical cell, when it is better conducting, will give a better result. So, vacancy material, you can see the black one in the impedance plot, that is E, having the lowest resistance value. As a result, we can say higher will be the conductivity, resulting in a higher activity of the material. And coming to the stability plot, that is F, you can see it can show with a continuous electrolysis of 20 hours. Now, we can the material is stable, it is not showing any decrease or increase in the potential value, that is 1.5. The best part of the material was like means what is the role of the vacancy, how it is affecting the electronic structure. So, we have done a DFT calculation which was done by one of our scientists, Brahmananda sir from BARC. We could see from density functional theory that the vacancy materials, iron orbitals contributing more density of states to the Fermi label and compared to the others. And because iron contribution to the valence labels are more, so and there are in the valence band, the contribution, the empty molecular orbitals of molybdenum, I am sorry. So, here the iron and contribution will be more in the density, the Fermi label. As a result, the conductivity of the material is increased. Also, the selenium vacancy also helps in contribution to the conductivity of the material. These are some optimized structure of the material, because intermediates, as I have told you, were oxygen oxygen radicals, then your oxyhydroxides and OH hydroxyl radicals. So, some of the hydroxyl of O and your OOH were adsorbed in the material. It was optimized, which helps to calculate the free energy of the material. With the help of the equation, it was found that the theoretical calculation which you have done, that is the potential value for this reaction, and the theoretical calculation, there was a good match between the theory and the DFT calculations, the theory and the experimental calculation. Similarly, fascinated with the vacancy, we also tried to create selenium vacancy in nickel selenide, iron selenide. In that, we have used 0.3 molar iron, but when we increase the iron above 0.5, even without taking 1 molar, it is converting nickel selenide, iron selenide instead of nickel iron 0.7, 0.3, like that which we have taken in the before case. In that, iron doping was done in the iron nickel selenide, but here both the nickel selenide and iron selenide is formed when iron concentration was increased. So, here the synthesis is we just used hydrothermal method using nickel and selenium metal source at 170 degrees Celsius to produce nickel iron precursor. It is not named as any LDH, it is just named as nickel iron precursor because XRD did not match with anyone. Then when we use selenium powder in that, giving using a microwave method for 10 minutes, after 10 minutes we could produce this material. And for vacancy creation, we have used hydrogen hydrate as reducing agent, and additional we have sonicated sonication power was given, so that selenium vacancy could be produced. Here also in the material it matches well with the nickel selenide, iron selenide, confirming the formation of nickel selenide and iron selenide. You could see the same pictures, it have a spherical structure, and the SAT pattern indicates the 011 plane of iron selenide, and the last one, the SAT pattern indicates the crystalline nature of the material. But when we had a treatment with hydrogen hydrate to produce vacancy, you can see there is a change in a structure. From spherical it has come to a flower like structure when vacancy is created. Here also in a XPS all the elements, that is iron, nickel and selenium were present. From the XPS we have calculated the selenium vacancy. In the table you can see the nickel +2 to +3 ratio in vacancy material is higher compared to the parent material. That only indicates the formation of selenium vacancy, because as the nickel +2 ions are increased, so overall positive charge get decreased and some selenium has to remove, so that there is electrical neutrality in the molecule. This is some of the electrochemical parameters. Here also the vacancy material shows the lower potential compared to the others, having lower Tafel slope value and lower impedance value, and the stability here also it is 20 hours. The mechanism which we could suggest is that as we apply the potential in a material, so electrons, since Gc is the anode which has the capacity to take the electrons, so since nickel +2 and iron +2 states are present, so electrons will be removed from nickel +2 and iron +2. As a result, nickel +3 and iron +3 will be formed. Since electrons is getting removed, the holes which is there will be utilized by water for oxidation of water. This is how the oxidation takes place in a water by use of holes in the material. And the selenium vacancy no doubt facilitates this transfer of electrons through the material through the vacancy site. Similarly, we have done a very beautiful work on nickel ferrite. What we have done is we modulated the nickel ferrite structure by using different surfactant. Then we have created vacancy to see the enhancement factor. So, what we have done is we have used various surfactants to produce nickel ferrite. The different surfactants that were used is oxalic acid, ascorbic acid, citric acid and no surfactant, named is as NFO, NFA, NFC and NF. So, NF stands for nickel ferrite. So, here also synthesis of selenium oxygen vacancy was done by using hydrogen hydrate solution as a reducing agent, and sonication were given to produce the oxygen vacancy. From all the structure different surfactants which we have used, we could see the oxalic acid where we have used, that is D, could give a very beautiful plate like structure. And once you can see it has a beautiful plate like structure, it have a more surface area compared to the others, also which was verified by electrochemical surface area we could calculate, and found that electrochemical surface area of the nickel ferrite used formed by using oxalic acid, that is D, you can see the picture, have a beautiful plate like structure giving a higher surface area. And more you know, the more the surface area, more will be the catalytic activity of a material. So, XRD conforms the nickel ferrite structure in all the materials used using different surfactant. B indicates the oxalic acid nickel ferrite, and C indicates the vacancy material, that is oxygen vacancy material in B, that is nickel ferrite formed by oxalic acid. And in C you can see the structure has a bit reduced compared to nickel ferrite oxalic acid, which have a plate like structure. And these are certain the other parameters like SAT pattern and your lattice fringes, which indicates that it have a crystalline structure, and also the 311 plane having the disk spacing of 0.251 is the equivalent to some of the peaks of iron selenide. Some of the peaks of iron nickel oxide, sorry. So, here this is the vacancy material where the structure is squeezed. 5 minutes more. Okay. So, XPS conforms all the conforms the oxygen vacancy in the material, and these are the electrochemical characterization which confirms the vacancy material is having a very good activity compared to the others. Since I have been given 5 minutes, let me move to another part of my talk, which is photophysical part, because this is a conference itself is optical spectroscopy. So, I will move to that one, skipping the other slides. Okay. Now, with the match with the theme of this international seminar, I will talk about something which I did during my PhD study, where we have used the photophysical part to characterize the molecules. So, what we did during my PhD study, which I did from IIT Kanpur, we have fabricated organic light emitting diode as for using the molecule which we have synthesized, and for that we require a fluorescent material. Organic light emitting diode has we know it has been used in various applications. We use organic TVs, organic LED watches we use. So, there are various applications in this. We have one cathode and anode from which electron holes come, and this combines in the emissive layer. That emissive layer we use to prepare which is a fluorescent material. So, in that cathode and anode gives electrons and holes which should match with the HOMO-LUMO label of the organic molecule, which is a fluorescent molecule or emissive material, and we prepare that. In that, hole and electrons recombine to form exciton, and that recombines in the emissive layer. So, that light can be produced from the emissive layer, and we could see various colors in our television screens or the screens where LED has been used. This is a beautiful material which we could produce, and Chemcom is the paper which we could get during that time. So, what we did is we have prepared di-benz-imidazolil benzene. You can see di-benz-imidazolil benzene, we can have a twisted structure where NH in one side is facing outside and the NH in one is facing inside. So, preparation is very like we use phthalic anhydride and orthophenylene diamine with polyphosphoric acid 180 degrees Celsius nitrogen atmosphere, maybe for 24 hours we could get di-benz-imidazolil benzene. This is blue in color. The above one I named it as DIBB, which is blue in color. When it is vacuum sublimed, it turned to green. So, we have di-benz-imidazolil benzene, which is a emissive material which used for organic LED. So, we could synthesize the crystal of that DIBB, which was blue color. So, and in that we could find that there was a intermolecular hydrogen bonding in the material. But once we vacuum sublimed it or heated it, we could see the green color in the material, but we could not synthesize the single crystal from that. So, this structure, what was happening, why the color is changing from blue to green, we were not having any idea, but the base the material di-benz-imidazolil benzene, which was blue in color, it was showing one intermolecular hydrogen bonding. And a unit structure, there was 6 molecules. In a IR spectra, DIBB, which is intermolecular hydrogen bonding, we have a broad peak for CH bonding, and when I heated vacuum sublimed and named it as DIBG, the broadness has decreased. So, we were thinking that what is happening, maybe the hydrogen bonding, intermolecular hydrogen bonding is breaking, as a result this is happening. The TGDTA also, the intermolecular hydrogen bonding part is having a higher stability of 500 degrees Celsius, but when it get heated the thermal stability decreases. the optical spectroscopy, that is adjuvants, we could see for DIB-B, which is blue in color, is having a lower wavelength, adjuvants wavelength compared to DIB-G, which is the heated product. And also fluorescence spectra could see the DIB-B having a wavelength of nearly 400 nanometer, but DIB-G, which was green in color, having 530 nanometer. So, when heating there was something was happening, and we thought that maybe due to breaking of intermolecular hydrogen bonding, there is a twisting of one part, as a result one of the hydrogen is coming near the other part, like I have shown you in the previous slide. See, both the NH were outside in DIB-B. As a result, the intermolecular hydrogen bonding was formed, but in DIB-G.
Sorry, you have to conclude.
Okay. So overall, finally, we could from the single molecule, we could fabricate one LED from the single molecule. Just by heating the material, we could get two materials having the not two materials, the materials having both blue and green emission, and LED was fabricated from the molecule, and we concluded that it is the intermolecular bonding is converted to intramolecular hydrogen bonding, resulting in such shift. With this, I thank you all for your presence and patience hearing. I must acknowledge Department of Chemistry, Utkal University. The funding agencies like UGC, DST and DST India, DST Government of Odisha and UGC. UGC was a funding from this organic LED material, and this DST, both the DSTs from Odisha and India were for the funding of electrochemical water splitting, which I am doing. I am also thankful to my collaborators from BISC, NML, Jamshedpur, IIM-10, IIP Dehradun. I am thankful to my PhD scholars who have already got the degree. First two got the degree, second one submitted the thesis, and other last four were working still now. And definitely my thanks to the organizers who could able to do this international seminar, and thank you so much.
Any question, please? So, one question from me. This nickel selenide, written in language, but have you studied the oxidation state? You claim to be +3, as I am inclined to believe.
Yes, yes, it is actually from the XPS state, you can see.
The original, before doping. I am talking of before doping, nickel selenide. What was its oxidation state? +3.
Before we didn't do XPS, only because you know it's very costly.
Because +3 state is very unstable for nickel.
Yeah, I understand, but definitely you can see we have some iron. The XPS will tell you that it's iron +2
No,
and
you have
+3
done the
states.
XPS after doping. I have seen.
Yes,
and charge,
it's
the
after
charge
all
balance that you have nicely explained. But I was
yeah, +3 state
stuck at
definitely.
that point.
Yes, sir, definitely +3 state is more of a unstable, but we could see there are XPS confirms the +3 states of nickel and iron in the molecule. Before
Thank
we
you.
haven't done that.
Our heartfelt thanks to Dr. Bijalaxmi Jaina for sharing your fascinating presentation. May I now invite our chairperson, Professor Sudhanshu Kosekhar Tripathi, convener Professor Dr. Deepa Nag, and organizing secretary Professor Dr. Abani Kumar Sahu to felicitate Dr. Bijalaxmi Jaina.
Thank you.
Please give a huge round.
Thank you. It's a pleasure to welcome our next distinguished speaker, Professor Dr. Ratan Kumar De.
এটা কাট দিয়েছে হ্যাঁ এটা কাট দিয়েছে
हाँ हेलो सो ठीक है अच्छा फॉरवर्ड कोटा अच्छा ओके so good afternoon to everybody. So let me thank Deepa ma'am and the head of the department Abani sir for giving me this opportunity to speak in this platform, and I am privileged to speak before Sudhanshu sir, who is my direct teacher, and I am more honored and privileged, you can say, because we used to speak before sir during our PG seminar, and now perhaps after 35 years I have the opportunity again speak before sir, and just let me take 1 minute, half minute to speak that sir was my internal guide at that time during my PhD also. Fortunately, he was present, and sir at that time asked me, Ratan, after this PhD, what exactly you want to do in research? And now I have the privilege to showcase some of my advancement in the research that I have done. Not all that I am not going here, only limited. And being the last speaker, one has opportunity or the that is called you can say advantage that your previous speaker already spoke so many things. And fortunately, my two previous speaker, they spoke both in the same line of this catalyst, and this is little bit area of the material science and technology, and not exactly we are using the characterization technique basically, which is intended for this conference, but our area is basically catalyst. I am working in the surface chemistry at Johnson catalysis for last more than 25 years after my PhD, and both the speaker, my previous speaker, they emphasized upon various kind of photocatalysis, electrocatalysis, etc. And in the same line, my work also more or less overlapping the same area. So basic things they have already told, but my area falls upon certain thing that is called, it is applied area, that is called I am working in the heterogeneous catalysis and bulk catalysis, supported catalyst, all these things I am working for the industrial purpose. That is what my work pertaining to. So this is our previously I studied in Stuart Science College as well as Ravensa College. So both the teachers are here. NC Pati sir was there, all my teachers are there, and fortunately sir is there. And I worked in Ravensa, and thereafter I moved to Central University of Jharkhand, and this is a beautiful place. You can see this, that is our this is top one is our old campus, and this is our new campus. We shifted to new campus. Now my more or less the talk will rotate upon this introduction, catalyst preparation, characterization, activity studies, all these things, but for industrial purpose. Okay. So I will only showcase what exactly we are doing. I will not go detail into characterization, etc. And maybe I will be able to finish my talk within 20 minutes. So you see, when we are talking about the catalyst, broadly it is divided into three types: heterogeneous, homogeneous, and another one special one, that is the biocatalyst, otherwise known as the enzyme catalyst, also enzyme catalysis. And my work is pertaining to the homogeneous catalyst, heterogeneous catalyst and bulk catalyst, supported catalyst. And if you see, when we are talking about the catalyst, basically we are talking about whatever my previous speaker they spoke about, all these things we are working in the lab, slowly it is getting transferred to the industry. And industry does not work in the way that we think, okay. And because it is a combination of the chemistry as well as the chemical engineering. When you are designing a plant, process plant engineering, obviously the laboratory work that you are doing, when it is transferred to the process plant engineering, many knowledge of the chemical engineering works there in reactor design and studying the heat transfer capacity, mass transfer capacity, all these things, fluid flow in general, all these things happens to be there. So, you require extensive knowledge of chemical engineering in addition to physical chemistry, material chemistry, inorganic, organic, whatever you can say. And now, why catalyst is very important? Already everybody has told you why catalyst is important. Just to supplement these things, I can say you that catalyst is nothing new. From previous time, much before this, from now time, you can say the catalyst was there during the fermentation, wine fermentation. It is a catalysis process basically. And these three names, as you see, these are a famous person in the catalyst. And catalyst, when you are talking about the catalyst, obviously you are talking about the Nobel Prize. And if you see a lot of Nobel Prize, all even in 2021 also, you see the Nobel Prize is from the area of the catalyst. Okay. It may be homogeneous catalysis, heterogeneous catalysis or the biocatalysis, but area pertaining to the catalyst. You see that in this, even in this platform, the all the topics more or less you see at least 20 to 25%, 30% topic falls in the area of the catalyst. So, you can understand the importance of the catalyst and catalysis process. And it is all about, you can see the journals, if you see all the Elsevier, SCS, whatever you can say, RSC, everywhere, catalyst journal are also high ranking journals. Now, when you are talking about the catalyst exactly, we are talking about the industry, because we are making the material. And heterogeneous catalysis, the most important thing is that we are playing with the surface of the molecules. Okay, surface of the molecule. We are applying, because understanding the surface of the molecule is most important. Sometimes we are able to understand, sometimes we are not also able to understand. We are taking the help of the theoretical consideration. So, maybe DFT, etc., whatever my previous speaker also said. So, those things we are taking into account to understand the mechanism of the catalysis, etc. Okay. And this SDG is one of the, you see, out of 17 goals, at least 5-6 goals are falling directly under the process of this catalyst and catalysis processes. So, how this topic is important to everybody, you can understand these things. Okay. Now, when we are talking about the homogeneous and heterogeneous catalyst, so obviously it is all about the finding an alternative pathway to complete the reaction, and it must be that the pathway provides a less energetic pathway. That is all the basic knowledge, graduation knowledge, intermediate knowledge we have. And the role of surface most important in solid catalysis process, solid catalyst, the role of the surface is most important, because the surface layer is the most important, where the catalysis activities takes place. It may be physiosorption, it may be adsorption, it may be chemisorption. We are applying so many models, so many mechanisms, but understand that sometimes, remember that the catalysis, whole catalysis process in the heterogeneous catalysis is all about the thermodynamics. It all about the thermodynamics. That is most important. That what I understand it. Okay. So, thermodynamics plays a very vital role in transformation of the molecule. Molecule A transport to molecule B. Molecule A is transferred to molecule B plus C. All this, where the understanding a thermodynamics process is most important. Okay. And now, when you are talking about the heterogeneous catalyst, when you are preparing the area in which I am working, lot of things are happening. So many, you can see so many parameters are there, TON, TOF, industries are using TON, turnover number, turnover frequency, selectivity, activity, so many terms they are using. Okay, you can get all these textbook knowledge, but when you are preparing the heterogeneous catalyst for industrial purpose, 2-3 things are most important. Okay. One is that components that you are taking. The components are active species, physical promoter, chemical promoter and supports. This is where the heterogeneous catalyst plays a role. And most importantly, the role of the support is different. It sometimes it that is you can say synergetically act with the material processes, and many of the industrial processes you talk any catalyst development, it may be BASF, it may be any other organization, okay, Clariant, etc. You can say that they very much secretly keep this chemical promoter, physical promoter. They will never tell you because this is the patented. Nobody will tell you. You see vanadium pentoxide. We know the vanadium pentoxide simple. It is transformation of the sulfur dioxide to sulfur trioxide. But how vanadium pentoxide is prepared? We know all of us know the structure of the vanadium pentoxide. But thing is that how exactly they are. But BASF catalyst they are making the same vanadium pentoxide. And in India, still we are procuring the B2O5 catalyst from the Germany or BASF. Why so? Because we are not able to prepare that catalyst which will give you 99.9% conversion of the SO2 to SO3. That is more important, 99.9%, not even 99.5%, because this point works a lot, remember it. So, here what happens, nobody will tell you regarding the chemical promoter, physical promoter, how they are working, and individually what is the chemical promoter works, modify the activity, selectivity, that is most important. Okay. And what this physical promoter, how they work, the physical promoter help in stabilizing the surface area. So, nobody will tell you, even if you go for the patent, nobody will reveal you how exactly this, how much quantity of the physical promoter, what kind of physical promoter or chemical promoter we are going to add for the preparation of the solid catalyst. Okay. And nano we are now talking about because the active metal species exactly we are reducing it and making it because it is all about the surface area per gram, meter square per gram. Obviously, we are playing with the surface. Okay. So, with this background knowledge, we are preparing the catalyst. So, the various catalytic processes, when you are making a catalyst, obviously, it is a chemistry. In chemistry lab, we are making a catalyst. So, we know calcination processes, then hydrothermal processes, then drying it, baking it, all these things are happening. Okay. But one of the things parameter that I am showing you, how each parameter, each process plays a role. Say for example, you take a calcination. We are preparing the aluminum oxide for example. Okay. Where this 300, 450, 900, 1000, 1200, I have taken it from a literature. You can see that if you just differ the temperature by 50 degree or 100 degree centigrade, the pore size of the material that varies. That is most important, and pore size is all about this heterogeneous catalysis, where the catalytic activity takes place. Okay. In the mornings, madam was talking about LDH, phyllosilicate kind of material. The D space is most important. I was just hearing the session. I happened to ask the madam that how that you are maintaining the D space, whether you are lowering it or that is called expanding it, exfoliating it, that is the question. This is where the role of chemistry or this chemical chemistry knowledge works. Okay. Now, when we are talking about now I will talk about the supported catalyst, and when I am talking about the supported catalyst, so many kind of supports materials are working. People are playing with. Clay is a support material, then other support material, for example, diatomaceous earth is a support material, silicon carbide is a support material, even carbon is a support material. So, according to their available surface area, we divide it into the high surface area support, low surface area support. There is not clear distinction, but act of a support selection, when you are selecting a support, the most important thing about the support is it must be inert, it should have a desirable mechanical properties, it must have a given a right kind of surface area, it should have a porosity, and the material must be stable enough, because the catalysis process happens, for example, industrial catalysis process happens, vanadium pentoxide activation temperature is 430 degrees centigrade. So, at that temperature the material must be stable, otherwise if you degrade, finish. And most importantly, the material must be low cost. So, that is where the knowledge of chemistry, chemical engineering, material science works. And now, when you are approaching to the industrial processes, from laboratory scale to pilot plant, then to industry, the following things, there are many parameters are there, many points are there, only 10 things only I have enlisted here. When you are, because stoichiometric reaction, because this is what the chemical engineer wants from you, from the chemistry person, stoichiometric of the reaction, temperature, pressure, concentration, phase of the reaction, thermodynamic studies, rate of the catalyst deactivation, regeneration, because the catalyst must be regenerated, otherwise they do not procure the catalyst. Industry will not procure your catalyst, because you see it is in a global competitive market. For example, I have given one example, vanadium pentoxide. Till India is not able to produce the right kind of vanadium pentoxide. You can tell me one company name. I have searched it, literature search, as well as I have contacted. They are not producing. We are all procuring from the BSF still now. So, you can understand the level of purity, level of selectivity and the activity of the material. That is where the things happen. And for example, physical properties, safety, environmental impact, cost calculation. This is the following 10 things at least a chemical engineer wants from the chemistry person, because this is to do the pilot plant study. This is what. Anyway, now I am going to, because one thing I have told you, one example I have told you, that the chemical engineering or the plant or the industrial plant does not work in the way we are thinking. Okay. For example, in chemistry knowledge, our chemistry knowledge permits that, for example, the production of methanol from the synthetic gas, the reaction thermodynamic favor at low pressure with increasing number of moles. This is fine. This is what our teacher taught us. We also read from the textbook. But in industry, the reaction is done at high pressure. That is where the difference is. The reason the methanol synthesis takes place at high pressure, 70 to 80 atmospheric pressure, because compressing natural gas is much less expensive than compressing a synthetic gas. That is what is the role, because industry wants less costlier processes always. Okay. Similarly, now we work with some support material, some bulk material, and to start with the support material, various kind of support material we have worked. So, 2-3 kind of support material, I will show you how we prepare the catalyst, where exactly we used it, okay, and in industrial purpose, okay, and the work carried out with in collaboration with the Indian Institute of Petroleum, Dr. Rajaram Ball, who is working in collaboration with the Reliance Petrochemicals, etc., to test the materials. So, we started with the red mud. Red mud, everybody knows it is a heterogeneous composition, and to understand the red mud property is very also difficult, because it is heterogeneous. The alumina industry in Nalco and the aluminium industry in Balco, they are producing the same red mud, but if you see the XRD or if you see the EDS spectra of both the things, little bit difference will be there. Okay, remember it. But red mud has one value, that is the utilization of the red mud is most important. People are utilizing it for the adsorption purpose, landfill, mostly landfilling purpose people are using. But because it contains some kind of very important minerals, so those has the potential to utilize it for the catalytic purpose, and we try to utilize it. How? Because this is the Bayer's process, how the red mud is produced. Okay. So, we incorporated certain kind of metal oxide nanoparticles over the red mud support. That is a simple thing that we have done. Okay. Of course, it took us maybe 2 to 3 years to understand how exactly it works. Only the final work I will show you here. So, you see, this is another kind of support material that we have used for the preparing a new kind of catalyst for the conversion of the transesterification process. This is your halloysite material. It is a tubular kind of material. I used it for the first time for the that is, I have modified it to for the transesterification reaction purpose. This is a hollow material. Okay. Now come to the red mud utilization. Red mud, just as I have told you in the beginning, I worked with the support production of the supported catalyst. Supported catalyst, simple that is called synthesis process. I have adopted using the CTAB as the surfactant. I prepare the that is called copper sol or copper nanoparticle, and then I incorporated over the red mud. Okay, activated red mud, doubly activated. AARM means doubly activated red mud. The activation process, a protocol is there. I followed the protocol, and then this is the hydrothermally we prepared this material, and we have taken the 10 image to confirm the material. We have prepared, and remember that the calcination takes place at the 550 degree centigrade. This is the final thing that I have shown. Okay, we calcined at different temperature also, but we did not succeed in getting the right kind of activity and selectivity. That is what I wish to tell you. Okay, so now characterization, various kind of characterization, because when you are preparing a material, as usually you need various characterization procedure, various data to confirm the right kind of material. So, these are the various kind of characterization procedure, out of which XPS is important, BET is most important as Purnendra was told, because surface area is most important. Without BET, you cannot do the heterogeneous catalysis process. Okay. And then hydrogen this temperature reduction programming, this is you required, XRD is a must, TEM is a must, because this is all about the material characterization. This all, and GC is a must, because thing is that when you are converting, you must know how much conversion happens, okay, in the laboratory scale. Now, we did the material that we have prepared, just I am showing you with the material we have correctly prepared, we did the TEM analysis, and you can see that the presence of the copper oxide, titanium oxide and iron in the catalyst material is confirmed, okay. In a particular, you see the nanomaterial of the copper oxide is there, already we have prepared, and now we try to utilize for the industrial purpose. Industry 2-3 various, we did the literature search obviously. So, after the thorough literature search, we tried with this conversion of benzene to phenol, and you know that benzene to phenol conversion right now industry, all the industry in India, they are doing it the cumin process. The cumin process is the 3-step process, very because it contains the hydroperoxide, so obviously this is the explosive process, very, and the critically the conversion percentage is 40 to 45% only, not more than that. So, we try to find out some kind of alternative with this. Okay. And this is a 3-step process. The most important thing is that this less reactive CH bond in aromatic compound is most important, which is not possible immediately. Okay. And we did the material characterization etc., which I am not showing it here, and we did the most importantly, that is the activity studies. And if you see the activity studies, when you are trying to convert it to benzene to phenol, it is not exactly it is converted to phenol, sometimes it is also converted to catechol, because another OH is also added there, okay, because due to over conversion. Okay. And this is where the temperature and the molar concentration is most important. Okay. We optimize the thing, and you can see that at least we get the 70 to 80% conversion, we got it somehow, but we cannot reduce the formation of the catechol somehow. This is we could not do it, that I must admit. Okay. And moles of percentage also we vary, and you can see the result. Phenol is there, but still I cannot say the activity is okay. Activity you can say activity is okay, but it reduced to some extent. Okay. But catechol formation still there. We cannot able to reduce it. That is the thing. But somehow we confirm that our material works. That is the important. And of course, we see the performance in different solvent medium, and you can see that 87.1 conversion and the selectivity, with selectivity, the conversion and selectivity is most important. Selectivity in acetonitrile, it is okay with us. Okay. That is we optimize this parameter. Okay. Now, we try to formulate a mechanism, because for chemistry people the mechanism is most important. The mechanism that I am showing you, this is we have confirmed from the DFT study. We supplemented with the DFT also. Okay. And somehow remember that copper, even copper is there in the red bar. If you say that what exactly we did in adding more copper, that is where the game actually, that is the game changer. We added different thing, but with copper with a particular more percentage, this particular conversion works. I cannot, this particular conversion works. It may not be, I may not be able to exactly mechanistically explain it why it did, because we try to take the help of DFT, but the result is that before you that we able to convert it. That is what. Okay. And of course, we think some also other paper they asked us, do you think that only copper is acting as a copper is only the ingredient there which is propagating this conversion process, because there may be titanium also. We don't deny it, but this works. Okay. Now, and most important is reusability of the catalyst. Reusability of catalyst up to 7th cycle we have tested it, and you can see that the even 80% of the selectivity is retained up to 5th cycle or more little bit. 7th cycle we confirm it. Okay. So, this is where our works click. Now, secondly, this work published in the molecular catalysis, we are also comparing the work with other processes. And now, another one work that we tried with, that is the conversion of the ethyl benzene to acetophenol. And what is the industrial difficulties that is placed before you? This is the industrial difficulties we have. Okay. So, we tried with the material, other material, and copper activated red mud in different molar percentage that we have done. And you see, even when you are trying to convert to acetophenone, benzaldehyde is there, you cannot eliminate it. Okay. And we characterize the material, we characterize with the BET surface area, pore size, everything we have done, and DFT study also we have done with respect to mechanistic aspect. And catalyst characterization is perfectly characterized, and you can see even S2TPR data also you can see, even the pore diameter data also you see, and the material time also you can see, everything is okay. But when you go to the activity, then at 75 degrees centigrade, for example, the acetophenone is there, but other converts, in addition to this also benzaldehyde is also there. But somehow whatever the other people reported, this is better than that, which can be at least considered for the commercial purpose. Okay. With some modification, little bit more modification, that we must vouch for. And activities we studied with different molar concentrations, selectivity and etc., with different solvent condition. Another 4-5 solvents we tried, just I have shown here 3-4 solvents. And we reusability test also we did, but here it is not more than 80%, it is 70 to 80% that we vouch for. Oxidation of the ethyl benzene to acetophenone, that is what we got exactly. Okay. And we established the that is called mechanistic aspect also. In mechanistic aspect, this mechanistic aspect is supported by this DFT calculation, and this paper got published in the New Journal of Chemistry, and widely very good, you can say the many people cited this paper, and we did the DFT calculation. We path A or path B, we selected is the path A is the right path. Okay. So now another one that we try to again, all this time industrial important, and we have we have given it to the Indian Institute of Petroleum. Dr. Rajaram Ball is connecting with the industry to that is called, still the process is going on. Okay. This is olefin epoxidation, and these are the following are the industrial difficulty with the olefin epoxidation reactions. Okay. And we tried the material, we prepared the material. If you see the this is a bulk catalyst, okay, and bimetallic you can say, and very simple synthesis procedure as you are doing in the chemistry lab. We characterize the material, time, XRD, everything we have done, and we confirm this material is correctly prepared with the JCPDS data also. Now we other that is called pore size, pore volume, surface areas, all these things are minimum parameter, as I have told you, the 10 parameter, that is with respect to this we have also studied this parameter, and surface area you can see not very high, but 77.93 is okay, it is acceptable to us. Okay. And then we try to find out the conversion, we use the DFT, because I have told you that to understand the mechanistic aspect, many things molecular modeling is required. We take the help of the DFT to establish the pathway by which the reaction happens in our material. And this green is the, if you see, this is the pathway which is the preferable one. I am not telling that it is the only one, but it is the preferable one energetically, thermodynamically, as you have studied from the DFT. Okay. And now we did all the characterization that I am not going into. You see the material preparation, so far as the bulk material preparation, you can see the time of the material, and it exactly shows the material is good enough, the particular size, pore size and nano size, for you can consider it for the commercial application purpose. That is where it stands exactly. And then we did the activity studies, which is the very important parameter, as I have told you, that 10 parameter. And activity studies, here it is most important that the order of reactivity, you can say this following is the order of the reactivity. That is where the things, and we started with the activities with various kind of chlorostyrene, cyclohexane, methylstyrene, nitrostyrene, styrene, all these things. Okay. But still somehow here also the problem is that we get sufficient amount of the main product, the byproduct percentage somehow we are not able to reduce. But anyway, it is better than the already reported data, that what I wish to emphasize upon. Okay. And now so far as the that is called conversion is percentage is there, you can see the conversion percentage. And then another one paper we tried, another one conversion, industrial conversion, which is a platform chemical, you can say, purpuryl to purpuryl alcohol. But when you are going to prepare the purpuryl to purpuryl alcohol, actually sometimes you never succeed because you ended up in the tetrahydro, that is called tetrahydroporphyryl alcohol. That is where the process lies. You try to prepare laboratory porphyryl to porphyryl alcohol, but actually instead of this porphyryl alcohol, either you get tetrahydroporphyryl or tetrahydroporphyryl alcohol. That is the main reason of difficulty here, industrial difficulty. We prepare the material here and we characterize the material. This is the nickel MRM, this is the modified red mud. This is different from the this doubly activated red mud. Okay, with same red mud with different composition we did, and we try to establish the that is called your mechanistic aspect with the DFT, and how exactly the hydrogen molecule is seated upon the surface of the material, that we try to understood. And this is the first time we did it, because you see when you are going to for the DFT of particular red mud kind of thing, it is very difficult because it is not a only one or two metal, it is a mixture of metal. So, the basis set a number of basis set. Actually, we are not able to do the DFT so easily, but we still try to do with the help of IIT BHU and Professor Indrajit Sinha, and we try to understand how exactly the hydrogen is sitting upon the surface of the heterogeneous catalyst. And this is the schematic model for the reduction of the porphyryl molecule. We found it energetically favorable. The detail you will can also see, and this is the minimized structure of the adsorption of the hydrogen molecule, because hydrogen must be, because hematite is in the right more percentage, that is why you took the hematite percentage Fe2O3 here. Okay. And then we optimize, we did the activity calculation, etc. Here also you see our percentage of the porphyryl alcohol is okay, but to some extent also we get the byproduct. I cannot say that we have not gotten the other product, but conversion percentage you can see far better, but to some extent FOL is there. Okay. Now this paper got produced, highly praised in the Dalton transaction. Okay. Now we prepared some supported as a bulk catalyst, one support I have shown you. So just to how much time, sir? 10 minutes? 5 minutes. Okay. So just I will show you what exactly we did. This is another one catalyst that energy. This is the biodiesel, the trans-esterification we tried. This is the 4E goals, you know, biodiesel, all these things, these are the textbook knowledge, you know, and why we are biodiesel we are preferring already, you know, this is the reduction of the CO, hydrocarbon, soot, pH, etc. And this is the manufacturing biodiesel limit. And here in India now 20% this blending is most important. Okay. So 20% blending, why it is important, you can, this data will say you why this 20% blending is most important than other things. Okay. All about the calorific value, all about the specific gravity. Okay. Now we prepared the material, because you can see that very simple material, zirconium oxide, this is we have prepared just as Purnendu was told by chemical method we have prepared. Okay. And we just with halloysite we put it. Halloysite, why? It is a tubular structure. Obviously, it is a good support, nobody has worked upon it. So we tried it, that is the thing. Okay. And we succeeded. This trans-esterification, simple, you can say that even we have done the DFT study, etc. we have done detail. You can say that simple material, you can tell me this is simple material, you just put DDR02 upon it. Yes, we did it, but this works, that is fine for me. Okay. And this is more than 88% conversion happens in trans-esterification reaction. We saw the literature, nobody has done it, we did it, we got succeed, and we characterized the material and we did it. And another one material that support I use, hectorite. You can see that hectorite is also another clay material. Nobody has done it, we did it. We did it with both calcium oxide and zinc oxide. We prepared the nanoparticle of zinc oxide, calcium oxide. Hectorite we put it, hydrothermal technique, simple material, and this trans-esterification we did. And detailed material character, very simple work. But somehow we succeed in trans-esterification reaction. That is where, because in this competitive world, who do the first, and that is where the game lies. Okay. And we did it. And you can see the most important here, in our catalyst, people have done it. But here I have told you one calcination temperature I have told you in the beginning, if you remember correctly. Here the calcination temperature, you see, the moment you are going to 800 more, the catalyst activity immediately reduces. If you go just more than 1000, the catalyst rapidly deactivate. That is where. And you see, when we prepare the catalyst within 600 to 700 degrees calcine temperature, the activity you can see. how the biodiesel yield is consistent. Now this is our biodiesel plant, exactly where we worked. You can see very simple design, but we did it, Indian made. We just prepare it with the local help, and this is the plant where we work. Now some photocatalyst work only we did. I will show you, because other all my previous researcher already did it. I am not going to the detail. These basic things Purnendu and both madam has explained you in detail. Okay, so these things I am switching over due to time lag, but we did it. This work we have done. Already Purnendu had explained a lot of things, but what I have done, what I have done, let me explain you. This is thing Purnendu has explained it, so it is easy for me. Just a minute. Why it is not working? Titanium oxide. Yes. You can see what we have done. Purnendu has told about the graphene, and the photocatalyst madam has also told. Here only we are the gold. So reduced graphene, titanium oxide. This is, you can take ordinary photocatalyst we prepared. That is in a particular mole percentage we gold we added. Okay, and our photocatalyst also we worked. We compared it, the data. This is the procedure how we prepared it. This is the procedure, simple procedure, chemical method. In laboratory we have done it. We characterize the material, reduced graphene oxide everybody knows, and we also prepare the same method, Amar's method. Okay, we characterize the material perfectly. Only thing is that we added the gold there. Okay, and this is the material we prepared, and the characterization we done, and detailed characterization, microstructural analysis. These things are TEM analysis, detailed we have done all these things. Rubber spectra, all these things just I am switching over due to lack of time, and charge carrier recombination Purnendu has told, electrochemical studies, all this detailed study we have done, ternary photocatalyst, just switching over to show you. This is one mechanism. This is the hypothetical mechanism, proposed mechanism based upon the DFT study we proposed it. How our material works. This gold loaded, this RGO and titanium oxide, that is the ternary photocatalyst, how it works, we have proposed it. And now coming to the summary and conclusion, the catalyst, all the catalyst material that we prepared, we tried to apply it for the industrial purposes. The 3-4 material in the previous one that I have shown, we went for the industrial processes with the IIP and future scope of the work. And this work got published in the molecular catalyst as well as the Journal of Hydrogen Energy. And there are also another 2 journal we have published. And advantage of our catalyst, these are the certain advantage of our catalyst, and most importantly, it has a reusable characteristic, regeneration capability, and has a commercial importance. And thank you for your kind attention.
Questions to Professor De. Hey, Gyana sir,
Gyana, yes. Give him the mic.
Professor De, why we are using transition metals as catalyst? Why not the other metals?
Transition metal D orbitals, if I am sure. Nothing DD transitions.
That's why.
I think that's the only reason everybody is using transition metals. If I am sure, the best.
Okay.
But the most important thing here actually, we play with the material using the support material, because this halloysite, hectorite, red mud, this is perhaps little bit we have modified it. If you see pure red mud, I have not used. Doubly activated modified red mud and halloysite activated, all this is where exactly the game lies. Thank you. Thank you.
Professor De, I am really amazed to find that from waste material you are converting into a high performing catalyst,
Yes, sir, it is.
heterogeneous catalyst, and with high selectivity and efficiency.
Yes, sir. So because
Kudos to you and your team.
no, because I am actually giving.
And what
thank-
Professor Ratan De I saw 30 years ago. Now it is a sea change that I am finding in your work.
Thank you, sir. I am very happy
amazed.
that I privileged to present my because sir has told me during the PhD Viva. I still remember that what exactly you are going to do, and perhaps after 30 years or 35 years, I showcase
so
some
proud.
of my work.
I am so proud and
for
I'm amazed.
Same guide, same teacher.
Thank you.
Thank you, sir. But it took me 35 years. Thank you, sir.
Sir, one question, sir.
Yes.
Sir, what is the modern uses of catalyst with role of temperature in inorganic or organic fields? Modern uses of catalyst, both in the field of inorganic or organic.
Catalyst.
Yes. What is the more innovative methods that catalyst uses in inorganic or organic fields? That catalyst has enhanced and decreased the both rate of reactions.
Yes.
But what is the major characteristic with temperature? That you told that at a particular temperature it can be stabilized, but within certain limited temperature or high temperature it can be destabilized. That what is the modern use that we come across in
Model use.
modern advanced use of catalysts in the field of
catalyst,
inorganic and organic field?
you see, catalyst, for example, catalyst is a field. First thing is that whatever your industrialization process happens, na, all catalyst.
Yes, sir.
Everywhere catalyst. You may talk about heterogeneous, homogeneous. Every field is a big field. You may talk about even biocatalyst, etc. And thing is, understanding the chemistry of the catalyst is some. As I have told you, I read so many theories, so many books, etc. Only one thing I understand: thermodynamics plays a vital role in all this catalysis process. From the beginning, I told you. And understanding thermodynamics is more important. And sometimes we are able to understand. If you agree, okay, Himanshu sir may agree. Thermodynamics,
Yes, sir, sir.
sometimes we understand, sometimes we are not able to understand. And that is why you are taking, because the collection of the data point is more important. कितना डाटा जैसे सर बोले आइसोथर्म के लिए कितना डाटा, 4 डाटा में आइसोथर्म नहीं होता है. You require a number of data.
Yes, sir. Yes, sir.
That
Yes,
is
sir.
where exactly.
Yes, sir. Thank you, sir.
Thank you. Thanks.
We sincerely thank Dr. De for such a thoughtful and engaging talk. Now I request our respected chairperson, Dr. Sudhanshu Sekhar Tripathi, along with convener Professor Dr. Dipa Nag and organizing secretary Professor Dr. Abani Kumar Sahu, to kindly do the honor of felicitating Dr. De. Let's all join together in a warm round of applause.
Thank you. Up next, I would like to call Dr. Smruti Patnaik, Associate Professor in Chemistry at UN Autonomous College, Odaspur. She has done her PG at Ravenshaw University, PhD on the topic of drugs in chemotherapy under the supervision of Professor UN Das, IIT Kharagpur. Currently, under her guidance, 5 students are working on a project in SOA University. So please welcome Dr. Patnaik.
A very good afternoon to one and all present here. Respected Sudhanshu Tripathi sir, my teacher, and respected sirs and madams present here, and my dear students. Today, firstly, I would like to give many thanks to organizing secretary, esteemed Professor Abani Sahu sir, and Madam Deepa madam, and all the faculty members of Department of Chemistry, Stuart Science College, and all my dear students. Today I would like to speak, my topic is hydrogen as future green fuel. So all my dear students, you all know that hydrogen and oxygen, these are the two elements which are very much essential to chemistry. Hydrogen combines with oxygen to give water. The 5 basic amenities of our life in chemistry belongs to chemistry. So what are the 5 basic amenities of life, 5 basic requirements of life? First is air, second is water, third is soil, fourth one is food, and fifth one is shelter. So among that, there is hydrogen as the future green fuel, my topic. My dear students, do you watch Gyana Vigyana Karyakrama in DD Odia? Pilamane DD Odia ro Gyana Vigyana Karyakrama jati dekhuthibo tahale sethire moro ei second episode re asibo hydrogen as the future green fuel. प्रथम जाइछि अंगारक एवं तार यौगिक मानकर व्यवहार, सेकेंड आसीबो हाइड्रोजन एज द फ्यूचर ग्रीन फ्यूएल. ओडिया रे पूरा प्योर ओडिया रे कहबाकू पड़िबो, किंतु ओडी इंग्लिश रे कहबी. Hydrogen is the simplest and smallest element in the periodic table. No matter how it is produced, it ends up with the same carbon free molecule. So it is very much essential to be carbon free molecule. However, the pathways to produce it are very diverse. Green hydrogen is defined as the hydrogen produced by splitting water into hydrogen and oxygen using renewable electricity. So what is green hydrogen? That is very much important for all of us. That is the hydrogen produced by splitting water into hydrogen and oxygen using renewable electricity. Then decarbonizing the planet is one of the goals that countries around the world have set for 2050. So what is decarbonization? Decarbonization means elimination of carbon dioxide or reduce the percentage of carbon dioxide in atmosphere. This technology based on the generation of hydrogen, a universal, light and highly reactive fuel, through a chemical process known as electrolysis. My dear students, you all know that. What is electrolysis? The chemical decomposition of an electrolyte by the passage of electric current into cations and anions. So that is the technique, a universal, light and highly reactive fuel, that is hydrogen, through a chemical process known as electrolysis. This method uses an electrical current to separate the hydrogen from the oxygen in water. If this electricity is obtained from renewable sources, we will therefore produce energy without emitting carbon dioxide into the atmosphere. That is called as what? That is called as decarbonization. Electricity and drinking water. Impact of green hydrogen. Hydrogen as a fuel is a reality in countries like the United States, Russia, China, France and Germany. Then others like Japan are going even further and aspire to become a hydrogen economy. Below we explain what the impact will be in the future. Energy storage. Compressed hydrogen tanks are capable of storing energy for long periods of time and also easier to handle than lithium ion batteries because they are lighter. Then transport, come to the point, transport and mobility. So you all know that. What does it mean, transport and mobility? Hydrogen's great versatility allows it to be used in those consumption reaches that are very difficult to decarbonize, such as heavy transport, aviation and maritime transport. You all know that what does it mean? Heavy transport, maritime transport and aviation. There are already several projects underway in this area, such as Hycarus and Cryoplane, which are promoted by the European Union and aim to introduce it in passenger aircraft. This is the power 100% by renewables. Then thank you all. Thank you all, my dear students. Lastly, I would like to say that, my dear students, you always want to know that, you always be tend to know that what are the green chemistry and what is the general chemistry we used in our daily life. You always try to know that what is general chemistry, because in our daily life we always use the general chemistry. Sir is my teacher, Sudhanshu sir is my teacher. In her polymer classes, sir told that man is itself a polymer. I remember that man is itself a polymer. So how man is a polymer, my dear students? You know that? How man is a polymer? How man is a polymer? What is polymer? A polymer is a giant molecule or macromolecule which is held together by means of large number of small molecules, and that is together by means of covalent bond. So man contains what? Large amount of flesh, large amount of blood, large amount of bone, etc., etc. So my dear students, man is a polymer. So you always try to know that what is general chemistry, what is green chemistry, because now the world is going to be greener and greener. Thank you all, my dear students. Thank you, thank you, thank you. Jai Jagannath.
Thank you, ma'am.
Hey, Sadie, hey, hurry. हाँ दिया मैडम को दिया सपोर्ट सॉरी चलो Respond please. Now just now we have a message from Rashtrapati Srimati Draupadi Murmu. The special message just now we have get message. The President of India SMT Draupadi Murmu is happy to know that Stuart Science College, Kotak is organizing an international seminar on current advances in optical spectroscopy and its application, Caosa 2025, on 26th and 27th September 2025, and also bringing out a souvenir to commemorate the occasion. The President extends her warm greetings and felicitation to all those associated with the Stuart Science College and sends her best wishes for the success of the event. Thank you.
Hello. I request all students to come front and occupy the seats. Kindly occupy the seats. Also, madam and sirs, come front and occupy the seats. Kindly, I request all of you.
ମ୍ୟାମ୍ ତ ନାହାନ୍ତି। ଏଇଟାରେ କହିବ ତାପରେ ଆଇ ଏମ୍ ବୈଶାଖୀ ଦାସ କହିଲା ପରେ ନେଇ ଏଇଟା ପାସ୍ କରିଦେବି।
Hello. 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 Hello.
ଏବେ ନୁହଁ ପରେ।
Hello. Hello.
ହ୍ୟାଲୋ ହ୍ୟାଲୋ ହଁ ଶୁଭୁଛି ଶୁଭୁଛି। ଚାହୁଁଛନ୍ତି? Friends.
व्हाट्सएप देख ये आमर मैम पठे जो कौन थी संस्कृति मैम से पठे जो विनर सर अबनी सर पचार फास्ट सेकेंड थर्ड कौन से सब पचर भितर कर पचारिक सेंसर देखिए कर व्हाट्सएप चेक कर
A very good afternoon to all the dignitaries present here. I am Sai Subbalakshmi Swai, PG second year student.
And I am Vaishakhi Das, a student of PG first year.
As we draw the curtains on this enriching 2-day seminar, Caosa 2025, it is the time for valedictory session. These past 2 days have been nothing short of inspiring, filled with knowledge sharing, meaningful discussions, and the exchange of innovative ideas. May I take the opportunity to extend a warm welcome to our chief guest, Professor B. Ravindran, sir. May I request you to please take the dais. To honor our esteemed guest with a symbol of love, respect, and a warm welcome, we would like to invite our volunteer to come forward and present a bouquet and badge. Now, I request our Honorable Principal Dr. Deepa Nag and our respected Head of the Department, Abani Sahu, Dr. Abani Sahu, and a dedicated Organizing Secretary. Now, I request our volunteers to please come and present bouquet to our chief guest and our Honorable HOD and Principal. May I now respectfully invite our Honorable Principal, Dr. Deepa Nag, to address the gathering.
Honorable Chief Guest, Dr. Balachandran Ravindran, Retired Director ILS, Professor Emeritus, Respected Organizing Secretary Dr. Abani Kumar Sahu, distinguished keynote speakers, esteemed delegates, respected faculty members, and dear students. As the sun sets on these two incredible days, I find myself feeling a mix of emotions, immense pride in what we have accomplished together, a bit of sadness that it is coming to an end, and great excitement for the future we have just helped to shape. It is my privilege and honor to draw curtains on this immensely successful and intellectually stimulating international seminar on current advances in optical spectroscopy and its applications, Caosa 2025. First and foremost, our profound appreciation goes to our chief guest for his visionary tone for this seminar, highlighting the transformative power of optical spectroscopy. Your presence has been great honor for us, sir. We are immensely indebted to our distinguished keynote speakers, session chairs, and all the invited speakers who traveled from across the globe. Your groundbreaking presentations, rich with knowledge and foresight, formed the very backbone of this event. My sincere thanks goes to all the delegates and participants, the heart and soul of this seminar. Your active engagement in technical sessions, the thought-provoking questions you raised, and the vibrant discussions in the hallways are what truly made this seminar a resounding success. I would be remiss if I did not acknowledge the monumental efforts of the organizing committee, all the teaching and non-teaching staffs, and countless volunteers and my loving students. These teams worked tirelessly, often unnoticed, to ensure the seamless execution of every detail, from abstract management to hospitality. Your dedication and teamwork have been exemplary. We also extend our gratitude to our sponsors and media partners. Your generous support was indispensable in bringing this international gathering to life. A special word of thanks to the management for their unwavering support, for providing us with the excellent infrastructure to host this event. As we depart, let us carry forward the knowledge gained, collaborations initiated, and friendships forged. Many the sparks of curiosity ignited here continue to fuel innovative research in fascinating field of optical spectroscopy. Thanks you for making this seminar a grand success. Thank you.
Thank you so much, ma'am. We come to the time when we would be felicitating our guest. We would like to felicitate our honorable chief guest of this event, Professor B. Ravindran. To do the honor, may I request our principal, Dr. Deepa Nag, and head of the department, Dr. Abani Kumar Sahu, to please present us the memento. It is truly said that science is not only a discipline of reason, but also one of passion, curiosity, and endless exploration. And today, we are deeply honored to welcome a personality, Professor B. Ravindran, who embodies all of these qualities. He worked as the microbiologist for more than 2 decades and was later Director of Institution of Life Science, Bhubaneswar, and marching his scientific career with deep interest and innovation not only in India but also in abroad like UK, USA, Germany, Netherlands, Malaysia and Indonesia for decades, working as a visiting scientist and publishing international journals. Professing his innovation by paving paths in the field of biotechnology for the generation to come. Over the last 3 decades, several PhD and MD students worked in his laboratory and placed in several institutions in India and abroad. He is currently engaged as Chief Executive Officer of IMJE NEX India Limited, a biotechnology company at Bhubaneswar. May I now humbly invite our chief guest, Professor B. Ravindran, to address the gathering and share your valuable insight with us.
Thank you. Well, I was very pleasantly surprised when Professor Nag approached me about a few months ago to come for this event. My first reaction was that I'm not a spectroscopy person. So I would rather start with a small disclaimer that my experience in science has made me use spectroscopy in multiple ways, but the science itself is something a bit alien to me. So I'll make this confession before I say anything more. But nonetheless, I was even more impressed with the activity in a college of this kind to be doing a seminar of this scale. When I received the program, I was immensely pleased to see the representation. I understand for a variety of reasons, not all the speakers came in person, but the technology allows you to be with them or for them to be with you very consistently. So that's one of the reasons why. But then at the end of the day, what matters is the quality of science that is being presented, whether in person or online. And of course, I'm glad that there are quite a few who have traveled long distances to be here with you within the country and outside the country, particularly in Africa. So, and this gives a certain level of confidence to people in the students particularly and the faculty. If a central university were to do this activity, I won't be surprised because that's their job. As a matter of routine, they should be doing it. And if state universities do it, even then it's an occasional event, but it does happen often. But for colleges to be doing this event is fairly unique. I must, yeah. And my compliments to the leadership and also the hard-working team which has managed to put together an event of this dimension for 2 full days. But then I have had this passion over the years to spend time with students. I feel so young when I end up in a gathering where students are half my age or sometimes 1/3 my age. You always get a nice vibe when you attend a program of any kind where you spend time with students. So I've never missed an opportunity to do this every time when there is an occasion, particularly even schools. I spend quite a bit of time visiting schools, spending time. When I was with the Institute of Life Sciences many years ago, I must confess, about 15 years ago, when science outreach was not very fashionable among science institutions in the country, we started an outreach center and we reach out to, I can't get the numbers right, every year more than about 6,000 students across different schools in the state. And there are many who come to spend time with us in the campus at least twice a year. And then there are students who come for specialized training. So we do this partly because our target, frankly, has been school students and the class 7 and class 8 and 9, because that's the time they take a call about what they want to do in the future. And there is a serious requirement to get people in science to the stream of science, particularly basic sciences, regardless of which subject. When science is not really fashionable for students, a lot of them go for technology-centric one or the usual other courses that people get busy with. So that doesn't happen, and one of the efforts that we have been making in all central institutions, research institutions across the country, is to sensitize students at a time when they are in a position to, not position to take a call what they want to do, but then there are societal pressures, there are peer pressures to go into one stream or the other. And that allows people to do what somebody else want them to do and not what they want to do. So even somebody may be passionate about doing science, but then they end up doing something else, partly because there is peer pressure. So one of the reasons why we do this, talking to students. And then, as I said in the beginning, optical spectroscopy. I've used multiple ones as an instrument for answers in biology, but not actually the science of spectroscopy per se. So the closest I went more recently was when I had a collaboration with a person in Indian Institute of Science, because we work on infectious diseases, medical problems, biological problems. When I had an opportunity to collaborate with a friend in Indian Institute of Science to see whether Raman spectroscopy can be used for diagnosis of infectious diseases. In the beginning it appeared very weird, probably we are wasting our time doing that for simple diagnosis of infectious diseases, because at least the Raman spectroscopy that was available at that time, I'm talking about 7, 8 years ago, 10 years ago, in Indian Institute of Science, a machine that occupies a whole room, why would you use that for diagnosis of an infectious disease? But then in the last 10 years, so much, there are portable versions, and that makes it easier. And sometime back, about 3 years back during the peak pandemic, we actually funded a BSL-3 compatible, when I say BSL-3, the biosafety level 3 laboratory where you can handle SARS-CoV-2 virus, where a Raman spectroscopy portable model gets into the BSL-3. And to that extent, the technology has grown dramatically in the last 10 years. You also feel little nice that after almost 95 years after C.V. Raman discovered Raman effect, it still seems to be giving us enough to think about and use the technology. So that's the level. The other thing that I can think of, there are people who have my friends who work on NMR, for example. They're very proud of the fact that NMR alone has produced 6 Nobel laureates in the last 100 years. So this is one particular technology which has been churning out one after the other for a variety of different purposes, the last one being for MRI machine. And MRI today is the mainstream of every diagnosis for dementia, for Alzheimer's disease, and a variety of neurological disorders, amongst other things. So because of the non-invasiveness of the technology, NMR and MRI technology has become so useful in a variety of ways. So in some ways, what people thought some years ago as a technology or a science that is outdated or there is nothing really much to do, all of a sudden you realize there is so much more to be done in optical spectroscopy. So it's indeed very appropriate that you have part of this exercise. I'm sure it will grow even more in the years to come. And thank you very much for letting me being here as kind of an outsider, but still nonetheless I feel very nice about it. Thanks very much.
Thank you so much, sir. We are grateful for your presence. We now come to one of the most exciting parts of any academic gathering. Yes, indeed, it's time for the prize distribution ceremony for the oral and poster competition conducted as part of this prestigious international seminar, Caosa 2025. Let's begin this award for the oral presentation category. May I request our chief guest, Professor B. Ravindran, our principal, Dr. Deepa Nag, and head of our department, Dr. Abanikumar Sahu, to kindly do the honor. And I humbly request my dear volunteers to cooperate. And the winners' names for the oral competitions are Kabita Behera, Madhusmita Jawab, Asit Kumar Pradhan, and Dr. Smriti Patnaik. I am repeating my winner's name: Dr. Smrita Patnaik, Kabita Behera. Okay. Sorry, ma'am. It's first Dr. Smriti Patnaik, Kabita Behera, Madhusmita Jogab, Ashit Kumar Pradhan.
Sorry, after Kabita Behera, I would like request to Madhusmita Jadab to kindly Madhusmita Jadab. Next, Asit Kumar Pradhan, kindly come to the dais and take your certificates and memento. Next, Dr. Smriti Patnaik. Next, for the poster competition, first prize goes to Pooja Das, Subhasmita Behera, and Subhasmita Behera and Archana Mishra. Thank you.
I request Archana Mishra to come to the dais. Now, as we come to the close of this insightful international seminar, I would like to request our head of the department, Dr. Abani Kumar Sahu, to deliver the vote of thanks.
Sorry. Good afternoon, everybody. Respected dignitaries, Honorable Chief Guest, Dr. Balachandran Ravindran, retired Director ILSA and Professor Emeritus, respected Principal and Convener, Dr. Deepa Nag, respected speakers, faculty members, researchers, and my loving students. As the shadow lengthens and this vibrant seminar draws to an end, it is both a privilege and a deeply humbling duty for me as the organizing secretary to stand before you and express our profound gratitude. The past 2 days have been a remarkable journey of intellectual exchange, and it is now time to offer a heartfelt vote of thanks to the many hands and heart that made this international confluence a resounding success. Organizing an event of this magnitude is akin to orchestrating a symphony. It requires countless individuals, each playing their unique part with precision and passion to create harmonious and memorable outcome. Today it is my duty to acknowledge every one of those invaluable contributors. First and foremost, we offer our deepest reverence and gratitude to our Chief Patron, Right Reverend Surendra Kumar Nanda Sir. Sir, your visionary leadership and unwavering support providing the bedrock upon which this entire event was built. Your guidance was our compass and your encouragement our fuel. Thank you for believing in us. To our esteemed chief guest, Professor Balachandran Ravindran, your presence graced this seminar with immense prestige. This insight you shared during your address have set the benchmark of the entire event and left an indelible mark on all of us. We are truly honored by our participation. Thank you, sir. My heartiest acknowledgement to our patron, guide and mentor, Mr. Samarendra Pramanik, Secretary GB, Stuart Science College, without whom I would not have gained the confidence to stand before you all. The extent to which he has supported us is beyond my capacity to acknowledge. To our esteemed patron, Advocate Mr. Bididas, we offer our heartfelt thanks. Your stewardship and the confidence you reposed in our team gave us the courage to navigate the complexities of international coordination. A special word of thanks must go to our dynamic and indefatigable convener, Dr. Deepa Nag. Ma'am, you have been the captain of this ship, steering us through calm and choppy waters with equal composure. Your meticulous planning, your relentless pursuit of perfection, and your ability to motivate the team at all hours of the day and night have been nothing short of extraordinary. This seminar is a reflection of your dedication, and I speak for the entire committee when I say it has been an honor to work under your leadership. Thank you. The very soul of this seminar has been the brilliant minds who shared their knowledge with us. To all our distinguished speakers, session chairs, and panelists, both national and internationals, we owe you a debt of gratitude. You traveled from far and wide, bringing with you a wealth of experience, groundbreaking research, and diverse perspectives. The intellectual richness you have injected into this event has elevated its quality beyond measure. Thank you for your excellent presentation, for engaging in spirited debates, and for enriching our understanding of optical spectroscopy. Thank you all. It is both a privilege and a deeply emotional moment for me to deliver the vote of thanks at the close of this insightful and enriching international seminar. Now, I would want to express my heartfelt gratitude to one of our resource persons, Professor Joydev Dinda, whose unwavering support and collaboration have elevated this seminar to new height. This invaluable assistance in shaping the course of this seminar will live in our hearts and minds for all time. Thank you very much, Professor Dinda. We are fortunate to have you with you. Thank you. My special gratitude to our dynamic speaker, Professor Bankim Chandra Tripathi, seedling of the international seminar. Thank you, sir. Thank you for giving the inspiration to us. At the heart of this occasion stands a person who has not only graced this seminar with wisdom and scholarship, but who has also shaped me personally and professionally. My revered teacher and mentor, Professor Sudhanshu Shekhar Tripathi, great. Sir, words fall short when I try to express my gratitude. To stand here today as the organizing secretary of this prestigious seminar and to have you, my teacher, as our keynote speaker and guide, it is an honor beyond measure. Your presence has elevated this entire event. Your lecture was not only thought-provoking but also deeply inspiring, setting tone of meaningful discourse over the last few days. On behalf of the organizing committee and with all my heart, I extend our sincere thanks to you for accepting our invitation, for sharing your invaluable insight, and for being part of this academic milestone. Thank you, sir. Your smile to the audience is excellent, and your entertaining song is mind-blowing. Sir, thank you again. Thank you. We would like to felicitate some other renowned scientists who have enriched the field of chemistry with their insightful innovation. The vote of thanks is not complete. Many more to come. It is very difficult task for me. But inside some, that is, will felicitate some person, great persons. Number one, Professor Dr. Swapna Shankar Naik, head of the department, SB Women's College. Sir, please. Dr. Gyanjit Rai. Next, Akhay Kumar Bhadra, Santosh Kumar Samal, Nalinikanto Sahu, Alok Mishra. All are, I think, absent. Will send their felicitation, I think. Next, Barsarani Das. Absent. Barsarani Das. Huh? Barsarani Das, yes. Advocate Barsarani Das. Thank you, sir. Thank you. Thank you, sir. An event of this scale would not be possible without the generous support of our sponsor and partners. You are believed in our vision and invested in this pursuit of knowledge. Your financial and logistical support was the fuel that powered this endeavor. We sincerely thank all our partners for your trust and collaboration. We hope this partnership have been mutually benefited and look forward to your continued support in the future. To our esteemed members of the media, we extend our profound gratitude. Your presence and diligent coverage have been instrumental in amplifying the discussion and key outcome of this seminar, transforming them from proceedings within these walls into the conversation with the wider world. Through your reporting, you have built a vital bridge between academia and the public, and for your role as essential partners in disseminating knowledge, we are truly thankful, all the media person. Thank you. As we bring this memorable international seminar to a close, it is my distinct privilege to offer a special word of gratitude to a group of leaders whose support was not just beneficial but absolutely foundation to our endeavor. My thanks today are directed to the esteemed head of the departments and active members, my friend Dr. Akash Sahu, and Captain Dr. Akhay Kumar Das, Sunil Rojar Bishwal, Amarnath Sahu, Animesh Das Patnaik, Prashant Kumar Mohanty, and all head of the department of different faculties. The success of an event of this scale is never the achievement of a single committee. It is a symphony orchestrated across an entire institution. And you, respected head of the department, were the conductor of your respective sections, ensuring that every resource, every expertise, every member of your team was aligned to support this common goal. Your role began long before the first delegate arrived. We extend our deepest gratitude for your unwavering institutional support. Thank you for generously allocating the inevitable resources, the physical spaces, the sophisticated audio-visual equipment, and the specialized expertise within your departments. Your willingness to share these assets demonstrated a profound commitment to interdisciplinary collaboration and the enhancement of knowledge that transcends departmental boundaries. A special acknowledgement is due for your most significant contribution, the people. You gracefully released your key faculty members and staff to serve on various subcommittees, trusting us with their time and talent. Your guidance and counsel during the panel of phases were invaluable. The wisdom you provided, drawn from your vast experience, help us navigate challenges and refine our strategies. You were our pillars of strength and our trusted advisors. Thank you all. In essence, you created an ecosystem of our support and allowed the organizing committee to dream big and execute effectively. You fostered a spirit of unity and shared purpose, proving then the department collaborating seamlessly, the institution as a whole achieves excellence. Therefore, on behalf of an entire organizing committee, I extend our most sincere and respectful gratitude to each and every one of you. This successful seminar is a testament to your leadership and your belief in collective achievement. Thank you for being a strong pillars upon which this event was built. While we have acknowledged many contributions to this seminar success, I would like to take a moment to offer a special and heartfelt vote of thanks, a group of whose work is absolutely bedrock of any smooth running event, our dedicated office staff. Badababu Mr. Devaraj Pandey, King David Behera, Sushil Kumar Pradhan, Haraspriya Bhatto, Saudamini Das, Abdul Qadir Khan, Nelson Behera, Sheikh Sajid, Rajati Raut, Gopinath Mohanty, Monalisa Das. To the unsung heroes seated in the desks managing the endless flow of paperwork, emails and logistics, we owe you a debt of gratitude that is difficult to fully express. You are the steady hands that processed every registration, the calm voices and answered countless inquiries, and the meticulous organizers who ensures that every certificate, schedule and document was perfectly in place long before anyone else asked for it. Your work, often performed quietly behind the scene, was the invisible framework that held this entire complex endeavor together. You managed the chaos with impeccable order and a professional grace that did not go unnoticed. Thank you, all officials. Badababu, Mr. Devaraj Pandey, who provided the strategic oversight to all other staffs, who executed the plans, and Grace, who built our digital infrastructure. Each of you formed a unbreakable chain of support. You are the unsung heroes who turned our ambitious plan into tangible, flawlessly executed reality. You managed the chaos with order, the strength with smile, and the immense pleasure with unwavering dedication from day to night. Thank you, Badababu. On behalf of the organizing committee, the convener and every participant who enjoyed a seamless and professionally managed event, I say thank you. Thank you for your patience, your perseverance and your profound commitment. This seminar success is not just in the ideas exchange on stage, but also in the impeccable administration that made it all possible, and that success in large measure to you. On behalf of the organizing committee, I deem it a great privilege to extend our heartfelt gratitude to Mr. Biswaranjan Mohanty, whose tireless efforts and effective maneuvering of all external responsibility greatly contributed to the success of this international seminar. Your dedication in coordination outside work and ensuring the much needed funding has been truly commendable. Without your constant support and commitment, this event would not have been taken shape in such a smooth and successful manner. We deeply value your contribution and sincerely thank you for standing as a strong pillar behind the organization of this seminar. Thank you. While we'll all live enriched by the intellectual exchange of the last few days, there is a person who ensured we could do so in environmental of order, beauty and smooth operation. It is my great pleasure to offer a heartfelt vote of thanks to Mr. Samaresh Das. We saw the clean pathway, we appreciated the clear signal and flex design, and we benefited from the perfectly timed logistics. What we did not see were the long hours and the quiet efficiency with which you solved every challenge. You have been the backbone of this seminar, and we are all deeply grateful. Thank you, Samaresh sir. Now, last but not the least, I would like to turn my attention to the backbone of this event, the organizing committee. My dear colleagues, the student and faculty members of the chemistry family who work tirelessly behind the scenes, from the academic committee that meticulously curated the content to the registration team that managed the influx of delegates with a smile, to the publicity and outreach team who spread the word far and wide, to the hospitality team that ensured our guests felt welcome and comfortable, to the technical support team, specially thanks to Mr. Sapanjit Raut, that managed the complex audio-visual requirements seamlessly. Each one of you has been phenomenal. You have burned the midnight oil, sacrificed personal time, and handled countless unforeseen challenges with remarkable poise and professionalism. This success is your triumph. Thank you, Sapanjit sir. Just as the spectroscopy methods plays a pivotal role in characterization of a newly designed material, so is the role of these members of the organizing committee in tuning the frontier of the international seminar. Today I want to take a moment to sincerely appreciate each one of you who form the backbone of this seminar. Dr. Number one, first one by one, to have a patience please. Dr. Sasmita Patnaik, your strategic planning and meticulous attention to detail from day one were the compass that guided us. Your ability to foresee challenges and your calm demeanor under pressure were invaluable assets that steered this event to success. You were the glue that held the many pieces of this complex puzzle together. And for that we are all immensely thankful. Thank you for being our anchor and our compass. Dr. Tanushree Patnaik, you are the central nervous system of our operation, constantly monitoring the pulse of every committee. From the early stages of planning to the final execution, you are the one connected the dots, ensuring the work with hospitality team was in sync with the scientific program, and the publication committee was aligned with the registration desk, and no critical task fell through the cracks. Thank you for our exemplary teamwork and scholarly spirit. Dr. Sandhya Sayantini Mohanty, your dedication in training, guiding and motivating your young students with evident in their professionalism and enthusiasm throughout the event. You are our reliable anchor, always present, always ready to step in, moderating session, engaging with delegates, providing insightful comments and offering a helping hand whenever it was needed. Your supportive presence strengthened the entire endeavor. Thank you for playing a pivotal role in the seminar. Sandhya, thank you Sandhya madam. Mr. Kavita Bala Mohanty, you are our go-to person for the simplest and most complex question alike. Your ability to remain calm under pressure, your proactive problem solving and your gentle yet firm reminders kept the entire team on track and focused on our common goal. Your meticulous attention to detail ensured that every participant received their certificate of appreciation or presentation accurately and promptly. Thank you for ensuring a perfect and dignified conclusion to their seminar experience. Thank you, Kavita Madam. Dr. Suchitra Mohanty, Your dual role was absolutely pivotal to the seminar smooth flow. You expertly managed the intellectual heart of the event through the oral and poster committee, ensuring a rich, timely presentation schedule. Simultaneously, your oversight of seating hall management guaranteed a comfortable and organized environment for all attendants. This seamless integration of content and logistics was masterfully handled, and for your exceptional diligence, we are truly thankful to Suchitra ma'am. Mr. Manos Ranjan Pradhan, a heartfelt thank you to you for masterfully managing two committees that directly shaped our delegates' daily experience. Your leadership for the food committee and ensured everyone was well filled with delicious and timely meal, while your attention to campus cleanliness provided a pristine and professional environment throughout the event. Your hard work behind the scene created the comfortable and welcoming atmosphere that was essential to the seminar success. We are deeply grateful, Manos sir. Mr. Santosh Kumar Samantara. A sincere and special note of thanks to our treasurer, whose stewardship of the seminar's finances was conducted with impeccable integrity and meticulous care. You managed our budget wisely, ensured every vendor was paid promptly, and maintained perfect financial records, providing the crucial social stability and allowed every other committee to operate with confidence. Thank you, sir, for being the guardian of our resources and for your invaluable role in this success. Dr. Santosh Kumar Nath Sharma. A profound thanks to you for expertly managing two vastly different yet equally critical domains. Your leadership of the Transport and Accommodation Committee ensured our delegates comfort and seamless mobility from start to finish. Simultaneously, your editorial push in shaping the seminar brochure and souvenir has given our discussion a lasting intellectual legacy. For masterfully handling both the journey of our guests and the journey of their ideas, we are immensely grateful. Nath Sharma sir. Mr. Samarpita Behera. A special word of thanks to you for your remarkable ability to manage diverse responsibilities. You are truly impressive. You ensured a flawless and dignified conclusion for our delegates through the certificate distribution, maintained a pristine and professional atmosphere via campus management, and enriched our intellectual environment with the creativity created Wall magazine. Your dedication to both the logistical framework and the scholarly ambience of the seminar was indispensable. Thank you for your multifaceted contribution. Samarpita ma'am. Miss Sanskruti Mohanty, a special word of gratitude to you for your leadership that was felt at every critical touch point of the seminar. Through the registration, you created the first warm welcome for our delegates by skillfully coordinating the volunteers, infused the event with energy and seamless support, and with the creativity curated Wall magazine, you added a vibrant intellectual dimension to our environment. Your exceptional ability to manage both people and presentation was fundamental to our success. Thank you for your tireless effort. Last but not the least, the hero of the seminar, Mr. Sandeep Kumar Pradhan. Mr. Sandeep Kumar Pradhan, my right hand. A special word of thanks to you for your exceptional work leading the editorial committee. Your dedication has given our seminar a lasting legacy through the meticulously compiled abstract book. Your keen eye for detail and commitment to quality have perfectly captured the intellectual spirit of this event, created a valuable scholarly record we will all cherish. Thank you for preserving the essence of our discussion with such professionalism. Thank you, Sandeep sir. Thank you. Many thanks. Thank you for your tireless effort. A very special note of appreciation is due to our 4 dedicated staffs. Mistress Nirupama Mohanty, Mistress Gayatri Tripathi, Mistress Sonali Raul, Mr. Sapanjit Raut, and Mistress Karsia Pradhan. Your contribution was truly the helping hand that kept the wheels of this seminar turning smoothly. While your primary role is in the lab, you stepped out and became the versatile backbone of our operational teams. We saw Nirupama Mohanty tirelessly assisting the registration committee, ensuring every delegate was welcome with efficiency. Mr. Sapanjit Raut was the ever-present support for the technical team, seamlessly helping with audio-visual setup and presentation transition. Your effort ensured there were no delays and that our speaker felt completely supported. Meanwhile, Mrs. Gayatri Tripathi was indispensable to the hospitality and certificate distribution teams, always ready to guide a guest of organized material with a smile. And Sonali Raul, your adaptability shown that you moved between helping with the wall magazine display and managing last-minute requests from various committees. What made your support invaluable was not just the tasks you completed, but the positive and willing spirit you brought to every challenge. You were the unsung heroes who filled the gap, anticipated needs, and worked tirelessly behind the scene. Your collective effort created a seamless or professional experience for everyone. On behalf of the entire organizing committee, please accept our deepest gratitude for your indispensable helping hand. This seminar success is a testament to your hard work. A very special and heartfelt word of thanks most goes to our 4 diligent lab attendant, Mr. Prasanna Mohanty, Sukanta Behera, Susanto Kumar Vishwal, Samuel Behera, and also Ramesh Rajesh. Your contribution through often behind the scenes form the very foundation of a professional and welcoming environment for our international guests. In the days leading of the seminar, we saw you working with meticulous care, ensuring that every corner of the department sparkled and every laboratory were showcased was an impeccable order. The flawless arrangement of sophisticated equipments and the pristine cleanness of the spaces did not go unnoticed. It spoke volumes about your pride in our institution and your dedication to your hard work. You are the unsung heroes who operate in the background, at the sign on our success is a direct reflection of your hard work. Thank you for your tireless effort, your unwavering commitment, and for being the steadfast pillar that supported this entire event. We are deeply grateful. As we bring curtains down of this seminar, we do so with a sense of accomplishment, but also with the hope that the connections made, the ideas generated here will continue to flourish long after we have all returned to our homes and institutions. It has been an absolute honor and a great learning experience for me to serve as an organizing secretary. I apologize for any inadvertent lapses, shortcomings that may have occurred during the course of the events. Excuse me if any mistake. On that note, I officially declare the International Seminar on Current Advances in Optical Spectroscopy and Application closed. We wish you all the safe and pleasant journey back home. Enjoy Happy Dasara. May we meet again on another such platform of knowledge. Thank you. Thank you. Once again. Sarve bhavantu sukhino, sarve shantu niramaya, sarve bhadrani pasyantu, ma kaschid dukkha bhag bhavet. Thank you.
Good evening, everyone. Sir has given thanks to everyone, but a special vote of thanks and applause to Sir. Thank you for your leadership and thank you for all the pain you have taken for this international seminar. It's a great success, sir. We can please have a round of applause, special round of applause for Sir. Thank you very much, sir.
Thank you very much, sir, for your wonderful address. We often see our professors guiding us with wisdom and knowledge, but today we get to see a different side of them. So please put your hands together and join me in warmly welcome Professor Sudhanshu Tripathi on stage to mesmerize us with a beautiful song. Sir, please.
This was a pleasant surprise for me. The anchor took my name at the end. When the conference, international conference, came to an end. I was really amazed with the short speech by Mr. Balchandran, Professor Balchandran. So exciting. Principal Ma'am, Dr. Deepa Nag, and my dear Professor Abani Sau, and all dignitaries, Professor Biswal, and all Dr. Miss Datta, Dr. Tripathi, Dr. Dinda, and all others who are sitting here. My job is to sing a song, right? Am I correct? But I swear that I am faking the smile that I am exuding is really a fake smile. Because from the morning, 9:30, I am sitting here with rapt attention to what the presenters were speaking, and with my age at the 70, I think my maybe because I will never go away without singing a song, but please bear with me if I make a mistake, because might be I will be losing the three important parts of a song, which Dr. Datta knows. He hails from his music family, a musical family altogether. That sur, tal, and what? Lawyer. Tinta jaka jinsa to have a coordination. Habani moro. I promise. I will try. Itne. Ye kamu no hatru goli podi. Goli podi mo hatru. Oh, I'm sorry. Are you able to hear and understand Odia? But I was told yesterday by Professor Sau that ethi pilamane sabu gaibe bhaibe apun mane tike rahibe. E kon this is cheating. Let me compose myself. Come to my sa. C sharp. This is, let me explain. This is on a Hindu mythology, Lord Sri Krishna, who is very naughty, who was very naughty. से कौन कले राधा एवं तांको सखी माने जाउथले माठिया मुंडरे पानी धरिकरी जाउथले ये बदमाश श्रीकृष्ण कौन कले ना गोटे ढेला पकेकरी भांगिले सबु तक पानी पड़ीगला. आर यू एबल टू हियर अंडरस्टैंड व्हाट आई एम सेइंग. सबु पानी पड़ीगला राधांकर शरीर दिहरे. से कंकरी मोहे मारी गगरिया फोड़ डाली मोरी सारी अनारी भिगोई गए रे. सब ओदा ही गला. मोहे पनघट पे नंदलाल छेड़ गयो रे मोरी नाजुक कलाइयाँ मरोड़ गयो रे. मोहे पनघट पे नंदलाल छेड़ गयो रे पनघट पे नंदलाल छेड़ गयो रे मोहे पनघट पे मोरी नाजुक कलाई मरोड़ गयो रे मोहे पनघट पे. हाँ मोहे पनघट